So, welcome to day 2 of Smurf, the Sanjay Mortimer RepRap Festival, the first ever UK RepRap Festival being held in the stunning surroundings of the Oxford University Examination Schools. Woo! Oh my gosh, we had a big day yesterday. We had incredible talks from titans of our trade, including Adrian Bowyer and Max Solin. And we were also lucky enough to hear from our SMF stars, as well as a beautiful talk about Sanjay's early years from Sanjay's mum, Shamala. We had thrilling robot races hosted by Sam Prentice, with Jean-Paul being crowned our champion. Don't know if you're here today, Jean. Our auction, hosted by the fabulous Joel Telling, raised over £20,000. Woo! Thank you. Grant from 3D Musketeers decided to shave his head for the SMF and raised over £4,700, which is about, woo! Today is packed with our fantastic sponsors showcasing their latest innovations, speeches from the hugely talented Andy Gleadhall, our friends Mike and Sam on E3D's latest Revo Roto, and from our panel, hosted by Michael Petch, asking some of your favorite content creators about the awesome 3D printing projects they've been involved with. Plus, we have an amazing raffle, which costs just £2 to enter and has a Voron 0.2, complete with a Revo hot end installed, kindly donated by Alan Mandrick of Mandrick Reality. If you want to buy tickets for that, just come to the SMF stand in the North School. Yesterday, I spoke at length about the man who brought us all here today, Sanjay Mortimer. For those of you who were here yesterday, don't worry, I won't repeat it all, but you can catch it on the live stream if you're interested to hear more. Sanjay was neurodiverse. This simply means Sanjay's brain was wired differently. It was what gave him the ability to think and do things that the average person cannot. The output from his brain was amazing, working at warp speed and with the rest of us struggling to keep up. He liked to call it his superpower. According to the Equality Act of 2010, neurodiversity is classified as a disability. But it is just a natural genetic variation, the countless number of which occur inside all of us and make us unique. Genetic variations determine so much about our traits, both physical and mental, and this variation is no different. However, this variation is not without its obstacles. It is well understood that neurodiverse minds can find traditional education systems challenging. It leads to discouragement and disinterest, allowing those creative minds to slip through the cracks, face hurdles in academia, and thus in their careers. This is why we set up the Sanjay Mortimer Foundation. When we lost Sanjay almost exactly 2 years ago today, creating something that would help all the mini Sanjays out there to overcome these obstacles seemed the obvious thing to do. Whether as a teacher in his early years or later in his career at E3D, Sanjay was about sharing, collaborating, and encouraging. So that is what we're focusing on. If we, as a foundation, can find and empower these neurodiverse individuals, building their confidence and belief in their abilities, the data suggests that they are far more likely to go on to further their education, find employment in an environment where they can grow, impact the engineering industry, and define its evolution, just like Sanjay. This is the ethos of the Sanjay Mortimer Foundation. As every individual is unique, the support we offer is tailored to each of our stars. It might be a grant to further education, purchase a resource or equipment to further their research and development, provision of hardware or software. It may involve finding them work experience or internships with our partners in the industry. Or it may just be to introduce them to a mentor to help, guide, and empower them. Yesterday, we heard from Zack and Theodora on how the SMF has helped them. In order to help more stars like them, we rely on your continued support. We invite support through donations, fundraising initiatives, collaborations, and partnerships within the engineering and technology sectors. Each and every one of you are likely to be in a great position to help us in some way, and it doesn't have to all be financial. Please do come and find me or one of our trustees on the SMF stand to discuss further. Not quite. Last bit. We are here today in this beautiful building in the heart of Oxford University, an institution which has produced some of the greatest minds in the world, but minds many of which have been neurodivergent. We're here to witness groundbreaking innovation from our favorite 3D printing companies and to honor a life that ended far too soon. Sanjay would have been absolutely gutted to miss this, but I know he's here with us in all of our hearts. There are hundreds of budding mini Sanjays out there right now, struggling against the issues neurodiversity can present and how the condition is misunderstood. For all his achievements in the field of 3D printing, Sanjay had a lot further to travel on his journey when he left us. Help us find our stars so that we can ensure they are given the chance to get to where their incredible minds are capable of taking them. Thank you very much. Founder of Pure Poly, a company renowned for its expertise in large format resin printing and now making strides in FDM printing. Mark Penn is here with us today to share the intriguing development of Magneto X and explore how open source projects are instrumental in shaping this innovative venture. Please give a very warm welcome to Mark.
Thank you. I'm nursing a cold right now, so please excuse me if I cough or if my voice is a bit low. If you couldn't hear me well, please let me know. I'll do my best to make it clear for you guys, all right? My name is Mark Penn. I'm from Pure Poly, and I'm just going to give you a quick overview of what I will talk about today. I'm going to do a quick intro about myself and my team. I'll talk a little bit about the core feature of Magneto X, how it started, the challenges we face along the way, the iterations, and how open source project influence the development of Magneto X, and then finally what's next for Magneto. So I'm a Taiwanese American. I grew up in Taiwan and moved to US when I was 15. I'm the founder of both Pure Poly and Attack. Pure Poly makes large format resin printing, and Attack was the Pure Poly's material science division, and then I decided to make a separate company making their own resin. So if you do resin printing, there's a good chance maybe you have used our resins. We're one of the top selling brands on Amazon. And so I have been coming to RepRap Festival since 2017. And this is the first time I'm in Oxford, but it does feel like home. It feels very comfortable to be here. And so this is me back in 2017 at MUF, which is Midwest Festival, and I was launching a DIY SLA printing kit. The person who took the picture is Joe from Malta. Some of you may know him, Joe Casha. And you can see Chuck, Filament Friday on that side. There's probably several people in this picture that's here today. And here's my team launching Phenom, the large resin printer, Earth 2019. Which is the Eastern Eastern RepRap Festival 4 years ago, and we got a good reception there. And so here's me with my Voron Trident system. And so the origin of Magneto X, it's kind of started unexpectedly. It was summer of 2022, and we're still having COVID lockdown in Shenzhen. And so one day, our team, the 4 engineers plus me, were locked into an engineering lab for 21 days. They just won't let you go, so you'll be a place a little bit bigger than the stage, and just 4 guys there, nothing to do for 21 days. And we did things that most of you would probably did or already did, which is watch a lot of YouTube videos. And one thing led to another. We started watching a lot of Voron build videos. Some of the contents are made by people who are actually here today. And once you watch enough of that, you want to build yourself. And being Shenzhen, the nice thing is that all the parts we can order will show up next day. So in that 21 days, we started building a lot of Vorons. This was one of them. And that just kind of our team's actually resin printing, but that got us started making FDM printers. And we really enjoyed it, and we started thinking, hey, maybe we could put a ball screw in there, and the question then led to linear model. So this is kind of how the project started. And this is the core feature for Magneto X. The linear motor, the X and Y Z-axis use linear motor, so there's no pulley, there's no belts. The size is 400 by 300 by 300 millimeter. And to go fast, we can't just have a fast motion system. We need a high flow extrusion system to go with it. So we came out with our own lens extruders with pretty high flow rate. We're able to hit about 75 millimeter cubic now with selected filaments. And then if you want to print fast, you better make sure the thing's well leveled. So we had to go, we went with low cell leveling and also with full independent z-axis. And finally, to speed up the development, we use Clipper and Orca. That really saved us a lot of time. And I'll get into the details later. So some of the roadblocks getting there. We actually started talking to quite a few of our friends in the community about the idea of using linear molder for 3D printers. And the feedback we got was it was going to be too expensive. It was going to be an overkill because the precision you can get down to 3 micron, but you have a 0.4 millimeter diameter nozzle. For a lot of people, that just doesn't make sense. And then there was also the question of supply chain. Even in Shenzhen, there's not a lot of supply chain for linear molder. There's a lot of solution provider, but if you're gonna make one that's cost effective enough for 3D printing at this price point, you're not gonna be able to find one. And lastly, there's just not a lot of reference point. So when we were doing development, even with Clipper, there's nothing to look up. Thankfully, Kevin, the founder of the Clipper firmware, was very instrumental in terms of helping us. A lot of time he doesn't know the answer too, but it's good to have someone who's very knowledgeable to bounce back ideas. And so why did we do it? I think we figured somebody has to take that first step, right? And so if we are able to make a cost-effective linear molder with good precision, then that will force the extrusions. People will make extruders, people will make filaments to make more precise material. Somebody has to take that first step. So we figure we do the first step, and then I'm sure other advancement will come along as well as on the software side. So that was kind of the impetus to push us forward. The iterations. So one thing we learned that the way you design your linear molder is highly depending on how you design the whole entire system. So it's like a chicken and egg process. You can't just have a frame and find like a step molder just to make work with it. So we basically have to build a new printer, build a linear molder for it, find out what's not working, and then we have to rebuild the system again. And we did that about 3 times total. And the other things that we think about how to reduce the cost is that the linear molder can be very expensive, and some of the features are too much for 3D printing. So what we did was we kind of look at the performance costs, how you bring a racing car parts into everyday car using. So we actually lowered the specs of some of the linear molder, make it maybe not as precise. So normally you can hit 1 micron. We actually change it so that we can hit, okay, maybe 5 micron. It's not as precise, but you can actually reduce the cost a little bit and still quite good for 3D printing. So those are the things we did, and we repeat the process for about 5 different machines before we actually get to a point we felt, hey, this can be commercialized. And this is kind of where we at right now. We can actually, this is running flow test, so we can actually hit 75 really reliably with a really clean extrusions. But since launch, there was a lot of distraction, and it's one thing to make prototypes that will work, and there's another thing to actually deliver the products. So that's where we are right now. We have to find that point where the print quality and the consistency is there for every printers before we can ship our pre-order. And we are working on a community version of the linear molder to go for other users, but we are not there yet. We want to finish the production before going forward. And then let me cover quickly the last points. So I thought we are one of the sponsors for Clipper projects. And it's been instrumental for us. The way you virtualize the hardware makes it a lot easier to develop new printers. So if you think about project, this is a good one to go. I'm sure a lot of you knows it already. But we had a really good experience with the team. And with the Oka slicers, its integration with Clipper was very intuitive. So that was a natural decision for us. It saved us a lot of time in terms of the front end. We didn't have to, risking another slicer to make it work. This is a good option. And finally, and I think Voron team's in the house today, actually makes. And we just got a lot of ideas from Voron Design, how it's easy to change parts. And we also learned from Voron teams that many of users are using printing ABS. So that's kind of led us to do enclosure to our own design to make sure that will work. We're not a sponsor of Voron Design, but we're looking to contribute parts back to the Voron Design so that, to be part of that community as well. And finally, we are going to release a community version of the linear driver. Hopefully, our goal is to actually have that so that other people who may not necessarily into 3D printing may be able to use it for other projects. I feel having that, the community version will be something with a lot of API exposed, so you can actually have a lot of more granular control of the motor. You can do more projects with it. But that will be something early 2024. We can't do that right now, but that's something to look forward to. And for our printer, Magneto, we'll go with bigger and faster version, but let's finish the delivery for this first. And that's the end of my presentation. Thank you for listening. I know my voice is very coarse, but I'm glad you guys pushed it through with me.
founder of Nevermore 3D, who's a passionate advocate for safer 3D printing environments. Nevermore 3D, known for its innovative open source printer filtration projects, has been instrumental in developing filtration systems that significantly enhance air quality around 3D printers. Today, he will enlighten us on the risks associated with breathing volatile organic compounds, VOCs, emitted from molten plastics, a topic of utmost importance for the 3D printing community. Let's extend a warm welcome to Anders, and as he shares his valuable insights into this critical subject.
Thanks. Let's speak about filtering the fumes, shall we? As you see, I'm Anders, the creator of the Nevermore project for the open source filtration solutions, originally sprung out of the Voron community. And when I'm not obsessing about filtering printer air, I work as a senior consultant, MD, mainly in clinical nutrition at Uppsala University Hospital, Sweden. But today's talk is quite different from having an apple a day. We'll investigate the risks of breathing molten plastics. So in order to do that, here's today's agenda. What's worse, particulate matter or volatile organic compound, VOC? We'll look at a few examples of common VOCs and their effects on the body. We'll check out the differences between the particles emitted. And are particles always solid and inert objects? And finally, some words on optimal filtration and recent Nevermore and filtration media developments, including, but not limited to, this Nevermore StealthMax HEPA and carbon filtration system that you can check out on Nevermore GitHub. So, there's usually a world of difference between particle and VOC. If we imagine a single cell in our bodies is like the planet Earth. A PM particle matter 2.5 micron smog particle would be like the moon, but a single VOC more like a large building. VOCs are small enough to have direct effects on the body's metabolism and functions, and that's why I've been personally more concerned about exposing my family to them. For a long time, I believe the size relationship was the same for 3D printing particles, but that there were these large inert plastic particles in the air and the VOCs that caused the ABS headache. But as we'll see, that's not quite true. Let's start with VOCs. They're small. They're molecules that are drug-like in their effects. They penetrate the cells and affect the body cell metabolism directly. Some are good, just like drugs. Some are bad, some are neither. And we can't measure them either. If we have a common VOC sensor in our printers, it would go off the roof from farting or boiling water in the next room, and barely register if we print and have high levels of benzene. And the molecules, as you see here to the left, are quite similar to molecules that occur naturally or that we eat with our food. Here's an example of bisphenol A, BPA, and we all know it's forbidden in children's toys and cups and stuff, because it causes so much harm and linked to hormonal disruptions and cancers and all sort of risks. Yet, it's eerily similar to resveratrol, the healthy stuff in red wine that extends lifespans. It would be much better if our printers emitted resveratrol. If we go a bit smaller still, here we have caprolactine and styrene. They're both very similar and very toxic, compared to vitamin B3 there in the middle. Molecularly, it affects the cell machinery in similar ways, or obstructing our regular cell machinery. So here's the conundrum. Many people are debating, or have been debating with me, is it the particles that are bad with the 3D printing fumes, or is it the VOCs? And if we have that view that they're either large plastic inert particles and compare that to the small VOCs that affect the cell directly, then I would personally say it's the VOCs. But as we will see, it's not that easy. In 3D printing, the particles aren't that large. There isn't that huge difference between VOCs and the particles. Let me explain. Here we have the Arctic 3D printer. It prints igloos up north. So solid ice filament is reaching the heated nozzle and building the igloo a layer wall at a time. As the water or the ice reaches the heated nozzle, the water next to the nozzle heats up and emits steam and ice matter to the sides. Not everything is turned into pure water building the igloo. And printer VOCs and printer particles works the exact same way. It's heated up and stuff gets emitted to the sides. So the question is, the escaping water vapor composed of the single water vapor VOC, or are the droplets of water worse? Which one is more dangerous? And as you're supposed to realize, they're basically the same thing. So solid chunks of plastic would be basically better to breathe. It would be deposited in our lungs, just like breathing stone dust or something for many years. In time we'll get pulmonary damage, but not acute toxicity. But styrene from melting ABS is not a plastic anymore when it's not locked into the plastic matrix. It's actually a liquid at room temperature. So any particle that's not plastic yet contains these chemicals are soft and available for body absorption. So when particles are not bound into a hard plastic matrix, when they're as small as regular cell proteins, and when they're in a non-plastic liquid phase, hovering around the air, these are not the particles we read about when we see articles about the smog in New Delhi. These are super small and have the exact same effects like VOCs. Here's a paper comparing the particles and the filament. And as you see above, the raw filament has quite a few or low peaks, showing that the components is inside a large plastic matrix. But when it's released into the air by the heat, all the individual components and even new chemicals are created. And these are absorbable by the body. And that's what we notice when we breathe styrene gas. We get acute toxic effects in our bodies, manifesting as headache. These are some common liquid phase particle fumes, from styrene to toluene and benzene, and I won't even try to pronounce some of them. These are the causes of ABS headache and long-term potential side effects. And as we know, if we inhale stuff, we get quite quick effects, like from asthma medication or even trying inhaling alcohol, you get tipsy very fast. Another issue is the heat. The more heat we apply, the more particles we emit to the sides. So research has shown that if we just increase the temperature when extruding by 20 degrees, we 10x the particle count for many common filaments, or double them for PETG. So using the Arctic ice printer example, there's way more steam generated when melting on higher heat. So what should we do about it when we need the heat for our exotic filaments or for better layer adhesion? Well, let's HEPA filter the exhaust with good HEPA filtering. Even if the HEPA mesh is much larger than the VOC, HEPA is literally like 300 to 500 nanometers in size, while the particles are just 10 to 100 in size, so they're much smaller. Yet the HEPA filter can absorb them from electrostatic forces. So HEPAs do help. But the things that get through the really small contaminants, they need the carbon filtering as well. And carbon is awesome, but it does come with a great drawback. When we need a heated chamber, that heat makes the VOCs dislodge from the carbon again. If there was a way to use the heat in the chamber to instead destroy the VOCs, and that's what I've been working on this past year. So, right now in my printer, I am using not the carbon anymore, which works like a magnet. We have the ingredients for a cake, and it binds to the carbon magnet magnetically. But as we heat the chamber, the magnetic force decreases, and the VOCs or the ingredients to cake can get loose in the air again. So I've switched to these purple pellets. It still binds the ingredients to cake, but when we add heat, it causes a chemical reaction, actually transforming the VOCs into new compounds and binding them irreversibly to the magnet. We get magnet cake. And this is the new Nevermore filtering media that we call Scorch. Starts out bright purple like in the pic above, and color changes as it's slowly being spent, reacting with the VOCs emitted from the printing. And the hotter the chamber gets, the better, more efficiency in the chemical reactions. We like to apply heat to make a chemical reaction occur. So for instance, it turns the dangerous styrene that's carcinogenic into a food additive, potassium benzoate. So you could likely eat the scorch afterward. Don't do that. And mixing carbon with the new Nevermore Scorch even increases the possibility of an even wider range of VOC absorption. Not every toxin binds the same way to filtering media. We're also working on some photocatalytic options where we use the same reaction that the sun uses to break down VOCs when we exhaust them into air. The sun UV light breaks up molecular bonds and turns VOCs into carbon dioxide eventually. And this we can use in our printers too, with shining UV lights on titanium meshes and creating reactive hydroxyl groups. But we're not quite there yet, but it's under development. And please join on Nevermore 3D or our Discord in evaluating these up-and-coming filtering solutions. Thank you for the attention. Feel free to reach out with any questions or join the Nevermore community and find your filtering solution.
who will be telling us about the various awesome 3D printing projects that they've been up to and practical uses of 3D printing. Obviously, we have absolutely no idea where this is going to go, do we? But first of all, a warm welcome to our host, Michael Petch. And I think I'll hand over in a second to Michael Petch to chair this panel discussion. And I think everyone will introduce themselves individually. So, over to you.
Thanks very much. Right, good morning, everyone. Good to see so many smiling faces, bright-eyed and bushy-tailed after a great first day. So yeah, I'm Michael Petch. I'm the editor-in-chief of 3D Printing Industry, and I will be attempting to moderate this panel. My experience is it can be a little bit like herding cats. So let's see. We're also going to take questions from the audience. So about halfway through, we'll start taking a few questions. If you've got something you're itching to know, save it till then, and I will make sure we get to ask you what's going on. So you probably all know these people. I'm pretty sure you know them. But just in case you've been living under a rock for a while, then here we have Ellie. Ellie is the brilliant mind behind the Coca Press, the chocolate 3D printer. Ellie's also, you may not know, worked with 3D printers ranging from $250 to $250,000. And she's also the engineering genius behind BattleBots as well and destroying the competition. Next to Ellie, of course, you know James. You know James Bruton here. James has done so much amazing content, so many amazing projects. It's difficult to know where to start, to be honest with you. So we're going to try to get to that at some point. But you've probably seen the open dog around. We're going to talk about a few more of James's favorite projects, including the Mobius strip tank as well, which I highly recommend taking a look at. Next up, we have Zack. Zack creates incredibly wild and frequently hilarious content on Void Star Labs. And Zack has, again, done a massive amount of projects, so I'm sure you've got some great questions for him. This man needs no introduction, so I will not introduce Pooch. But I can confirm I have met him IRL, and he is cool. This guy knows probably more about Prusa printers than maybe anyone but Joe. So, you know, he's your go-to guy, really nice man. And then last but no means least, rather disappointed Matt didn't actually fly in on his jetpack at the back of the room there. If you've not seen that, there's a working jetpack. Yes, that's right. It's 3D printed. It's there. He's also got his preferred mode of transport, his Lego buggy as well. So I recommend checking that out. And you may not know, in addition to all of that, he's also worked on Star Wars. So wow. So let's go a quick round of applause to the panelists today. Matt, you're on the end there, so let's start with you a little bit. Maybe you can tell us a bit about how did you get involved working with Star Wars? What did you do there?
How's that? Can you hear me? Is this working? Closer? Okay, how's that? How's that better? Okay, all right. So the Star Wars thing, yeah. So I've done my real job, my day job is I work in animatronics, creature effects specifically, and I've done that for 30 years in the film industry in the UK. So we do animatronic puppets, robots, droids. We cover prosthetics, makeup, all that kind of stuff. Mostly sci-fi fantasy films. So I've done Harry Potter's, Jurassic World's. But for the last 10 years, it's pretty much been Star Wars back to back. Started in 2013, got a call about a new character, which I thought might be R2-D2, but I thought, well, it's not new. I know they're going to have to rebuild it, but it's not new. But it turned out to be BB-8. So I was part of the design team and build team for BB-8. And then I got to perform him on set as well. We had radio control versions and puppet versions. We built 7 of them for the first film, and really exciting after that. Myself and Josh, my partner in crime when it comes to building things, we built the red carpet BB-8 so that we could go to a premiere, because we were like, they're not going to want a puppeteer trailing along behind BB-8, but if we build one that actually works without anyone near it. Yes, some of it was 3D printed. Yeah, well, actually the first one was fiberglass shell, but there was 3D printed aspects. But the Mark II red carpet BB-8 was fully 3D printed shell. Yeah. So yeah, that's how I got into. Well, that's not how I got into creature effects, but that's my background in creature effects. I did electronic software engineering as an apprenticeship when I left school. Didn't really like academia, didn't get on very well, and saw that ILM used to use electronic technicians for model making and stuff, and I got a job as a model maker. I was a terrible model maker, but I could do electronics, and I moved up.
Follow-up question, are you looking for apprentices?
Yeah, I get that a lot. It's really hard because Lucasfilm are quite funny about having people, they won't take people who work for free, and a lot of people go, oh, come and do it for free. And it's really hard to get positions and like internships and things like that. And also, we're all just freelancers. Although I've worked technically for Lucasfilm Disney for 10 years for my boss, Neil Scanlon, he's in freelance as well. And so when the project ends, we all just go home and go off and do something else, like build giant go-karts and jetpacks. But then we come back and reform for the next project if we get the call. So it's not like a permanent setup where we can take internships. It's a really tricky thing to do. So yeah, sorry, not at the moment.
Sorry about that. All right, Pooch. So you've done so many things. Maybe you could just tell us about just one thing that's brought you the most joy. One project that's really sort of like dear to you.
Okay. Sorry, I've lost my voice, of course, already. I would say if I have to pick one thing, I'm particularly passionate about maker entrepreneurship. So for me, trying to find ways to do as much as possible with as little resources as possible. So I started my company looking for a niche in 3D printing, and I didn't want to touch making a printer with a 10-foot pole. But I said, okay, where's some opportunity? So I started making storage boxes and racking and whatnot. And honestly, I've gotten a lot of joy out of just creating the systems of learning how to manufacture on our own and build and grow from there, and talk to others about their maker journey and have conversations around that too. So I guess that's one.
That's one. That's bringing you joy. That's good to hear.
I love it.
All right, Zack, I want to ask you, just in case someone's not heard of Gridfinity, what is Gridfinity?
Gridfinity is hello? Mic check. Hi. Hi. I mean, my voice is loud, but it's not that loud. Oh. Yeah, you take the one that doesn't work. Gridfinity is a modular 3D printed storage system that's like a combination of base plates with a 42 millimeter slot and storage blocks that are comprised of 42 millimeter blocks. And the idea is any base plate will fit any storage block, so you can configure it as... why am I explaining this? Everyone already has one. Everyone already has like 3 of them.
This is true.
Raise your hand if you don't have a Gridfinity setup.
Okay, well, you have a personal audience then.
Brooke is giving me the dirtiest look. She's like, why don't you ever print me anything?
Well, maybe in that case, if we all know about Gridfinity, and I think that's agreed, tell us something we don't know about.
About Gridfinity? Or
Ooh, what's it?
Let's think. There's a few random fun facts about Gridfinity. I'm not sure. This one you don't know if you haven't watched my last episode, but the Gridfinity model, the original template, actually includes a track to fit RGB LEDs. Because originally the whole thing was going to have ergobleds built into it, and I ended up cutting that in part because I figured most people wouldn't want that, and also in part there wasn't enough surface area; it kept peeling off. So in my last episode, I ended up using that, but no one's ever mentioned it to me before. Like no one's ever like, hey, why is there like a 12 millimeter track carved into the bottom of every plate? Now you know that's a secret. Another secret is the idea of having the magnet holes also have little holes inside them for screws was a really terrible idea because it means there's a little dangly bit of plastic and you have to use support material. I know. So people ask me all the time, why don't you like fix that? Like, it's because I'm lazy.
I don't think the next man can be described as lazy. I don't think we can describe you as lazy, really, Zach. But James, again, it's difficult to know where to start with your projects. You've done and continue to do so many things. What's your favourite project, though? Maybe you can talk us through that. Tell us maybe a bit about the challenges you faced as well in building it.
It's hard to choose, really. Yeah, the favourite projects are usually the ones that do best on YouTube, because that's kind of my job, is to make things for clicks. So I think the one you mentioned actually is the Mobius strip tank that did really well recently. So a Mobius strip is a one-sided object. So if you get a strip of paper and you make a loop, but you put 180-degree twist in, and then you try and follow that side round, you end up on the outside, then it twists around, you end up on the inside. So it's only got one side. Someone in one of the YouTube comments said that we should make a tank with a Mobius strip track for some reason. But they didn't know why, and I don't know why either. But it seemed like it'd be cool for people to click on, so I did it anyway. And the only thing I could come up with was that you could have a whole track length of one type of driving surface, and a whole track length of another driving surface. It's still the same side, so there's a transition point at some point. Yeah, that's it. But what I've also realised is where the twist is, the track goes vertically, so then we can go and bend it. So I did a bendy track that was like a sushi restaurant conveyor belt. The next one's going to twist, and then it's going to bend the top and the bottom, which undoes the twist, so it won't be a Mobius strip anymore.
I love that. We weren't sure why, but we did it anyway. I think there's a motto there for a few people in this room, for sure.
We don't do things because they're easy, or we thought they'd be easy. We don't do them because they're easy. We do them because they thought they'd be easy.
So is the next version going to have Klein bottles?
So, someone said do a Klein bottle pulse jet. But I think that's something more for Intexa than me.
All right, let's come to you next, Ellie. You've had a bit of experience with robotics as well, haven't you? I mean, we know it over here as Robot Wars, but back in the States, it's BattleBots. So how did you get involved in that?
Is this on? Okay, I got involved by being in the right place at the right time, or maybe the wrong place at the right time, because it takes up so much time. I've been watching BattleBots for years. I always wanted to be on BattleBots, and I think the way I go about getting involved in things is I just mention it to enough people until it maybe happens, right? So if I mention chocolate printing to enough people, eventually someone is like, okay, here's some money. Can I have a printer now? So I met some people at Midwest RepRap Festival. They invited me to another robot combat league, and there happened to be an open spot on the BattleBots team that was closest to me in Baltimore, 2 hours away, and I started commuting to Baltimore 3 days a week and building battle robots, and then 16 days in Vegas for filming. It was, don't go to Vegas for 16 days.
So there you go. Support your local or international RepRap fair. That's what it's about.
Yeah.
Matt, let's come back down to Earth for a moment here, back from the galaxy far, far away, and a bit closer to home. You've done a really interesting project on a very remote island called Palau. Where is Palau, and what did you do?
So Palau is in the West Pacific. So if you heard of Guam, people might have heard of Guam. It's got an American base there and stuff, and Palau's further west than that, towards Indonesia. It's a tiny island. It's got about 17,000 Palauans and maybe 2,000 immigrants, expats, whatever you want to call them. And it's a fascinating place. I got to know about it about 2 or 3 years ago. My girlfriend was working out there, and I went out on holiday and stayed there for 6 weeks. Met some really interesting people, one of whom was a guy called Chris, who is sort of one of the senior lecturers at the community college in Palau. And last year I was going to go back out there for a month. I thought maybe a month or 6 weeks. It's a long way to get there. It's like a day and a bit's worth of travel. So anyway, on the way there I was thinking, well, what am I going to do? I had some ideas. We did some work with drones when we were out there. We were teaching rangers how to use drones instead of speedboats to patrol the areas and stuff like this. But I didn't think that was going to happen again. So on the way there I thought, I wonder if they have any 3D printing on the island. And when I got to San Francisco, I met Chris in San Francisco. We had a week there. And I was like, do you have 3D printers? He's like, I don't think there's a single printer on the island at the moment. I was like, right, this is my mission. So I contacted Lulzbot, who have sponsored me over the years and supported me with projects, and Polymaker. And I said, I'm going to an island, you know, this is pretty remote, and they have no 3D printing facilities. There's a community college. I want to set up a little makerspace there. Will you support it? And they were great. So Lulzbot sent me 5 mini printers and a TAS6. Polymaker chucked a load of material at me. It took like 3 weeks to get it through customs and all sorts of shenanigans. But anyway, I set up this little project space and a little maker space in one of the rooms on the island, and I went to schools and did talks as well. So I had anyone could come to this maker space, any age. And I also went out and did talks at schools, and I donated printers to 2 schools after doing a talk about 3D printing. We did projects. The students were doing stuff like they have a problem with rhinoceros beetles in the island. They're non-indigenous to the island, and they invade and they kill the palm trees. So they trap them, and then they kind of do work on them. They take them, dissect them basically, and work out where they've come from and things like that. So we 3D printed stuff for rhinoceros beetle traps. We 3D printed these little traps for fruit flies, which go on top of bottles, disposed bottles that are being thrown away, like plastic Coke bottles and stuff. So you recycle them into fly traps. And I went all around the island to atolls, installing them, and it was just a fantastic experience. And they're still there 3D printing now, so that was amazing.
Yeah, I think a lot of people can relate to that desire to put a 3D printer everywhere as well, but maybe you've taken it a little bit further in this case. So, does anybody here have a question for our panelists? Please, if you want to raise your hand, I can come to you with the microphone, maybe. Here we go. Right. Let's go. Here you go, sir.
Thank you very much. Quick question for Zack. When you're not reading a script, what's actually on the heads-up display?
Oh, all right. Is it working now? All right. Can you hear me? Hi? Hi? Can you hear me? Can you hear me? Yes. Oh, Jesus Christ. So the question was, what do I actually see on the heads-up display? Is that right? It's basically, it's basically just like white text kind of floating in midair. And the challenge is that the heads-up display actually is a really wide field of view. So like you could fill up a huge amount. So I have to restrict what amount of the screen the text can appear on. Otherwise I'll look like, I'm looking back and forth while I'm reading the script. And it's very important that I'm always looking at the camera. This creates a second problem where the more I tilt my head, the higher chance it glares. And this pisses people off so much. One glint and I lose viewers. That's basically what I see. It's just an Android phone basically, and I'm running this app called Elegant Teleprompter, which is designed to display text backwards because you bounce it off of mirrors or something. Yeah, the whole system is really like bending over backwards to work the way I need it to. But at least I didn't have to write it myself. It's the best part of this project. I didn't have to write any code.
What do you see when you are not reading a teleprompter on there? What are you looking at right now? Are you reading a book?
I can't. Wait, is this going on YouTube? Do we have to worry about being monetized? All right, then I can't tell you what's on it. No, it's just an Android device. Right now it's not showing anything. But usually if I were giving a talk, for instance, I would use, I forget the name of the app, but basically it controls a PowerPoint presentation and it shows me my notes in the next slide and lets me control it. So I get to look like I remembered all of my lines and I rehearsed all my script while I'm strutting up and down the stage, even though I'm just reading my crib notes. It's a real Ron Burgundy situation because I get into a groove and I just read whatever's on it. So oh man, that's another funny story. I'll put notes in my script throw Quagsire in from off stage or chuckle loudly, and I'll forget I'm not supposed to read that. So I'll just be that's why we're hacking electronics into Christopher the Quagsire. Throw it in from, oh God, not again.
I think I might need one of those for next time. Any other questions? Right, here we go, sir.
This is for Ellie. I was just wondering, how are you getting together with chocolate manufacturers? Are they approaching you for different types of chocolate and potentially having a multi-flavor sausage kind of situation going on.
This guy's in the future.
Meat flavors, meat flavored chocolate. Was that the question?
What did you say?
It wasn't meat flavored chocolate, was it? That wasn't the question.
No. Okay. Making those cocoa cores is a pain in the butt. You go to a chocolate shop or a chocolate manufacturing company, and you say, "Hi, I want this within X thousandths of an inch." Well tolerance because I'm using chocolate as a mechanical seal and no air bubbles, less than 0.5% of air bubbles. And they just look at you, no seams on the side, no mold seams. They look at you and they're like, what are you doing? Okay, we think we can do this. I have spent multiple years trying to get someone else to make them. It doesn't work. So we brought all the equipment in-house. Actually, Zach and Brooke referred somebody to me who now does all of my chocolate work. But that wasn't your question. Your question was, are chocolate manufacturers approaching me about using their stuff? There's definitely a shop in LA that uses their own chocolate. They've been using the same chocolate in their shop for 50 years. So they sent us a whole bunch of their stuff, said, we want to buy your printers, but only if it can print our stuff. We validated it, found temperatures, found settings that worked, and I believe they're still using it in their shop. In terms of multi-flavors, I want to get that working. I don't know how with our current setup because it would have worked, but when we started shipping printers, we scrapped our entire chocolate production line and started over about a month ago and bought about $15,000 of new equipment. It's been growing pains. I don't know if that answers your question at all, but with the new setup, it's a lot harder to do that.
So IDEX chocolate printer when?
Well, I have a spare E3D tool changer. I won some printers at the auction, so I have to get rid of printers, says my partner. And that one is staying. So maybe a chocolate tool changer just for fun for me. And for YouTube videos.
Who wants to see that here next year, huh? Yeah, okay, well, no pressure.
How do you ship things?
James, we've got the open dog over there. If you've not seen it, go and check it out. You've seen it. That video's got how many millions of views?
What, an open dog?
Yes.
That's version 3, and there's been 7 altogether actually of test dogs. They didn't do especially well though, like they're not really viral videos, but I kind of saturated YouTube with building robot dogs, so...
I think your definition of not very well is...
There might be a million views between all the videos, if we're lucky.
What's next for the project though?
What, sorry?
What's next for Open Dog?
Nothing at the moment, because I'm going to be doing bipedal robots. So the last video that went out was a little bipedal robot that's inspired by those Disney, the Disney Park, Star Wars Galaxy's Edge. They've had these... Oh, sorry, I pressed mute. I'll keep my hands off it. All right then. Is this better? Oh, that sounds better to me. Amazing. So Disney Imagineering came up with these little robots that have been walking around. They've been all over social media, and lots of people have made comments. Could I build one like that? It's quite a complicated thing to build. So anyway, I decided to start really simple with just 4 motors, and see if I could get this thing to hobble along. And so I did some walking robots in the past. I did actually a Star Wars gonk droid, but that was kind of when I didn't have so much budget and I didn't know what I was doing. So I didn't have any inverse kinematics that calculates all the joint angles, and I was just like fudging angles from an inertial measurement unit, measuring the angle of the thing onto some of the joints and trying to get it to hobble along. This is about 6 years ago, but since I've been doing the robot dogs, I've learned quite a lot more about what you're actually supposed to do with robotics, and now every video is sponsored, there's more budget. So moving from £10 motors in the gonk droid to like £300 to £400 dynamics or servos, and doing inverse kinematics and all the stuff. So it does just about hobble along, and it was surprisingly easy to get it to work. So it's kind of joint limited, so it can't sway its hips. It's like leaning a box on its corners.
I think you need to stand up and do that demo, actually.
Yeah, so the next thing will be to put these joints in. But at the moment, it does this.
Great move.
So that's what's going to happen next year. And then I'm quite hopeful I can make something that appears to do almost the same as Disney on flat ground. It won't walk through the woods or climb over rocks or anything like theirs does, but it'll be all right. I mean, I've only spent 2 weeks on it so far. There'll be another 2 weeks, and then...
How long, Matt, did you spend on the jetpack? And where's that going? Because that's incredible.
Sorry, how long did I?
Your jetpack, it's going up, hopefully.
It's going up.
Exactly.
Yeah. Going up very fast. So the jetpack company started about 2 years ago, just over 2 years ago. In that time, I probably spent about 8 months on it because we had 2 grants, government grants. We had funding. And I've said, I did another project called the Mantis, which was a huge 6-legged walking machine, and I did all that for free for 3 years, and I said I'd never work for free again. So the jetpack, I've stuck to my guns, and I'm like, no, if we run out of money, I'm going to stop. So it's been 8 months of work. But in that 8 months, we got the prototype over there, and I've done a lot of work in physics simulation, so that flies in a physics simulated environment very well, but it's quite different taking it to the next stage, because when you start... you try and switch that to you're burning 3 litres of aviation fuel per minute, and it's 130 decibels. The fumes are choking. I mean, you fill this room in seconds. You wouldn't believe how loud it is and how much fumes they give out. Both James and I have flown the gravity system, and it's the adrenaline that kicks in when you hear those engines. Just the noise alone is unbelievable. So that's where we're stalled at the moment. 2 years of work, 8 months of actual work on it. But I have got a patent on it, which is really nice, and that was part of the 2-year process. But now we're stalled at the point where you need a lot of money to get to the point where you can test it safely and get rid of all those toxic fumes and everything else with it. So it's got a little way to go. But technically that should fly. I just haven't plucked up the courage to fire it up. Should
Technically,
fly.
I like
Theoretically.
Technically. All right, everyone up here has undeniably done some pretty wild and amazing projects. And now you've built careers to different extents in the world of 3D printing. Let's just go down the row, maybe starting with Ellie. And everyone can just maybe give us some pearls of wisdom, some jewels that maybe other people are out there thinking, how can I get started? How can I kind of get more involved, make more 3D printing in my life? What would you advise people? Things you've overcome, maybe?
I agree with Pooch. Don't ship hardware.
Don't ship hardware.
It's actually really fun, but much more difficult than I thought it would be. I don't know what advice I would give. I think if there's a problem that you're trying to solve, all design is redesign, so just Google everything. Because innovation is really, in my opinion, most innovation is just putting together different things that already exist, and you just don't need to reinvent the wheel.
That was before Google. So before Google, I think Google killed innovation. I have a different view on this because when I did the
I like this hot take.
So when I did Mantis,
yeah, they got rid of Google News.
When I did
my
Mantis,
RSS
there was
feeds.
nothing out there. Like I had to go and buy books and read about inverse kinematics and do it and figure it out for myself. And if I'd gone online, I'd have never have done it. So
Are you literally dropping a back in my day on the?
I didn't realize there was a time before Google. I'll be honest.
There was a time before the internet.
How did you email?
Listen, young lady. we had to walk uphill both ways.
We had to go to the library. It was hell.
Just while we're on this topic, actually, could we all just tell my little girl, read more books?
Yes, read more books.
There you go, Nessa. Sorry.
More Reddit.
James, same question to you. What advice would you give?
To get into 3D printing or into making in general.
Making in general, getting into 3D printing, getting a career based around 3D printing.
Oh, okay. So, I mean, it's kind of different for me. I did actually do a toy designing job doing prototyping before I did this. And before that, I worked in IT. So, I mean, yeah, going back to before YouTube, basically, I had a day job for 10 years in IT. And then RepRap project came along. Arduinos and Raspberry Pi and all that stuff came along. And YouTube came along. And I put all my stuff on YouTube. And then I left my IT job because a toy company found my YouTube channel and wanted to recruit me. So I guess that's a really good way to get a career, doing something like this, is put it online So I'm quite single-track mind about just content production, and that's really what I do. Someone asked me if I have loads of, 3D printed things around the house to, I don't know, organize the cutlery or solve household problems, and I couldn't think of anything. I've got very little anything like that at all. Everything I do is about, projects and getting stuff out there. So yeah, from a career point of view, I think it's often these sorts of careers like the movie industry or the toy industry, you say those are really hard things to get into. But from having been in the toy industry, the reason is that most people are rubbish. And graduates come along with the same old university project that everyone's got the same textbook example. The one person who comes along with something they've done that's special, then you know that's the person.
So I mean, if you were to sum that up, maybe you could say, just do it. That could be a good slogan, I think. That might catch on. I don't know.
Yeah, come to a show like this. Get a 3D printer, get an Arduino and have a go.
Zach, any words of wisdom, any sort of advice?
I mean, if you want wisdom, I'm not your guy. But I guess I would say the biggest piece of advice I can give is finish your frickin' projects. So if you're anything, so like a lot of people are like, I lose interest in my projects after 2 weeks, right? How do you stick with it? And I'm like, I don't. I finish the project in 2 weeks. Like this means two things, right? The first is you gotta build projects. You gotta start projects you can finish, right? Don't. A lot of folks are like, oh, this would be interesting. If you're gonna learn something, learn it. But if you're gonna build a project, make it something you can do. If you don't, if you only have 10 hours a week to work on your stuff, build something you can finish in 10 hours. The second part is don't get too sidetracked, right? Like the problem with 3D printers are an awesome tool, but it's very easy to get caught up on the printer itself. So, before you do any upgrades or anything, keep in mind, like, what am I trying to do? Is my goal to, if I'm building Nerf blasters, right? Will this upgrade help me jam out more Nerf blasters? Because if not, it's not worth it. Stay focused on the Nerf blaster. If the printer is your project, be honest about that, right? You don't need a pretense to be into this, but don't. If you fired up the printer to build something, don't let the printer itself consume all your time and money, right? You got to remember what you started with. It's you got to remember what you set out to do and what your constraints are to do it. I know nobody likes to hear it. We all like to get sucked into stuff, but at the end of the day, nobody sees the unfinished projects, right? Like the things that inspire other people and get other people involved and put you on the map are the things you finish and you tell other people about. So get it done.
Get it done. Pooch, question to you, and also clear up on aisle 7.
Oh, you don't want to give up the mic?
You don't want the aisle 7 microphone.
So I have to add first a comment, and then I'll give you my tip. But one of the things that's interesting about the 3D printing, we talk about the 3D printing community all the time, and yet it's such an interesting tool set, right? Because the 3D printer is like the modern day hammer, right? And everything is that nail out there that we just want to print. We use the printer for everything because we can. But nobody talks about the drill press community so there's something very special and unique about this tool set, right? So my tip though is, while it's tempting that we have this fantastic machine that allows us to iterate and create things, it's not necessarily the best tool for the job all the time. And I know it might not be popular, okay? But if you're serious about doing something for business or whatever, hold on. Don't reinvent the wheel. There are lots of other things out there that you can do that are already off the shelf that you can supplement with your printer, rather than trying to print every little thing along the way.
It all yourself.
What do you think?
Use other people's models too.
Zach, microphone.
Oh yeah, don't forget, you can use other people's models. You don't have to cut everything you make from whole cloth.
With attribution.
Oh yes, you do need to tell, yes, of course. You got to credit the authors. But you're not obligated to do everything yourself. Like my last couple of videos, both heavily involved modified versions of other people's models. And both times, I caught myself starting from scratch and being like, why the hell am I doing this? Like, why am I working on a frame to hold a Raspberry Pi 400? I'm sure there are 100. I'm sure there are a dozen of them out there, right? Why am I working on an enclosure for this display? Like, I'll just download someone else's and tune it up. No, you don't have to invent everything yourself. And of course, you don't have to 3D print it all, too. If something is easier to buy at a hardware store, buy it at the hardware store.
Okay, thanks for the picking up the drill press community there. Shout out to all the drillers, I think, as they say. Matt.
I think that it is too easy for rapid iteration. You're right, and I never use my CNC machine anymore, but there's times I should. But the thing so when I was in Palau, the thing I tried to push across to all the students was we have a 3D printer now, but learn CAD. Because people go, right, I'm just going to download baby Groots and start printing plastic ornaments. But my whole thing was like, well, you're on an island where spare parts are rare. Learn how to draw the part. CAD is the most important bit. Now you've got the tool to make it. And that's the thing I was trying to put across to them all the time. And I actually had a Libra sponsored me as well. And they sent me a load of free seats, educational seats for the CAD. And I taught them a Libra design. And a quick story, so the local vet heard that I had 3D printers on the island, and she became one of my best friends, and she just amputated a cat's paw, and she said, could you 3D print me a cat's paw? And I did, and I taught the students how I did it, I showed them how I did it, I made it parametric so it would fit different cats. It turned out the cat was fine with 3 legs. That's not the point. We made it a prosthetic paw. But the sad part of the story is the one night I left the students alone. I went home early. They were like, "Yeah, we're going to stay behind and do some 3D printing." I thought, "Yeah, they're going to start CADing stuff and making stuff on their own." And I came in the next day, and they didn't realise that the last model you print is still loaded up. So I went in, fired up the machines, and the model came in. The first thing a student printed in Palau was a very basic weapon, and I was like, "Really?" I'm not going to say what it was. It wasn't terrible, but it was a weapon. So then I had to go, right, everyone bring it back to my desk. In the morning, I want them all back on my desk. And they were like, well, they broke anyway because we didn't need to use enough infill. And I was like, oh. So anyway, so CAD is the thing.
Field testing is very important.
Yeah.
All right, I'm not sure how much time we have left on this panel, but okay, that means we've got time for a couple more questions from the audience. Here we go. All right, coming to you.
Yeah, go for a walk. Leave us alone up here.
Hey, this one's mostly for Zack, or only for Zack practically. Have you ever thought about doing a full control generator for Gridfinity?
Oh, all right, so the question is, have I thought of doing some sort of generator utility for Gridfinity?
Full control. Like, you're talking about full control XYZ?
Oh, like using the multi-axis printer. Oh, man. Well, I couldn't because no one has them, right? Like, it's cutting edge stuff. As a matter of policy, I try to avoid doing stuff because it's cool. I do stuff because I want the end product. That said, full control is super rad. Honestly, though, like the Gridfinity design has a lot of problems, and I do wonder how, whether it could be printed much faster using like topological printing and multi-axis. It is interesting. I'm still my mind is still blown at the VOS mode one, honestly. I mean, like, damn, it uses like a fifth of the filament of my design. I feel like a jerk. Oh man, I have wanted to try it out though. I think for the base plate, it's a lot more interesting than for the bins itself. Because a big problem with the base plate is it really likes to curl. If you print it flat against the plate, it really doesn't want to stay on the plate. So it would be really cool to print it like sideways, using a technology like that. Instead of having to like bridge it out 42 millimeters, only having to do it like one layer at a time. It is pretty spicy. The cool part of Gridfinity though is that I don't really need to worry about all this because sooner or later someone is going to do it for me. Right?
Get a hive mind. Do we have another question? Here we go.
You said earlier that you had an Android phone powering that
Yes.
teleprompter. Is it in the device, or do you have it in your pocket connected to the, like the?
All right. So the question is like, where's the computer part of the heads-up display?
Yeah.
It's It's right here. So I actually revised the heads-up display design. I revised both the heads-up display design and the belt pack design. They are both all 3D printed, of course. Yeah, because basically, so my original design, the one that appeared on my channel, was only intended to be used in the workshop, right? It was only designed to be used in the studio. So as I started to do more and more trade shows, I realized that it wasn't going to fly. So I've made some major changes. So now the heads-up display is modular, so I can let people see it without having to take off the whole headband. And I split the belt pack into two to make it easier to, like, for instance, sit down, and so I can hot swap my batteries without even breaking the flow of conversation.
Smooth.
Perfect. Yeah, so it's right here. I'm sitting on it. It's more powerful too. I did end up upgrading to the the Codis Edge 2, which is so much better. This RK3588 chip is like, it's so good. Gotta try out the Raspberry Pi 5 though. I gotta see if that one's strong enough because the Pi 4 was not cutting the mustard.
All right. Do we have any other questions here? Anyone would like to know anything from our panelists? Right, well, in that case...
I have a question for Matt really quick.
Pooch has a question. Here we go. Get settled in.
How many three-legged cats are on Palau to warrant a parametric model of a cat's paw?
Just one, but it's very important.
That's not really the point. The point is they now have a leg that cats don't need in Palau. Because cats are really good with 3 legs, it turns out, and 2 legs even, actually. But... yeah, there are, to be honest, animal rights aren't great in Palau. They do, they're not fantastic with animals, and cats are about the lowest. Dogs are seen as quite high, but again, they're not that brilliantly looked after. So there are quite a few. My friend Pam, the vet, is doing an incredible job. She's kind of went out there volunteering. She does get paid now, but she just spends all of her time looking after animals that are being deserted and all that kind of thing, and run over and just left because people can't afford to get them fixed. So there are quite a few legless animals in Palau.
There you go. I learn something new every day.
Does that answer your question?
It does. It does.
Thank you. You're satisfied with that answer. Don't want to go deeper. Okay. In that case...
Well, I'll tell you what the future of animal-based electronics is, right?
Oh, please tell us. All right.
Oh, yeah. Heads-up displays. Heads-up displays for dogs. Dogmented reality. It's the future.
Heads-up displays for dogs. Right, this is going to be your Sunday.
3-legged dogs or 2-legged? What? 3 legs?
Reality. Huh?
3 legs or 4 legs?
I mean, that's the beauty of it. Like, it's all virtual. The dog doesn't need any legs at all.
So it feels like we're beginning to reach some big conclusions here.
We've hit a certain point here, I think. So look, everyone, please give a massive round of applause for Matt, Pooch, Zack, James, Ellie, and of course for our hosts as well. Thank you, everyone. Great.
Thank you guys very much. Thoroughly engaging conversation. Really appreciate it. And another round of applause for our wonderful host.
Good afternoon, everybody. So next up, we have two very familiar faces, Sam and Mike of E3D. These are two of our principal engineers, and they're going to be giving us some detailed insights into a new extruder that E3D has just released called Roto. They're going to be telling us a little bit about what sets it apart from other extruders, so please give a warm welcome to Mike and Sam.
Hello. Coming through? Okay. So yeah, as Josh said, we're going to give you... Closer? Oh, closer. We're going to give you a bit of a run-through of Roto, which is our new featherweight extruder. If Mike can just go to the next slides. So the stuff we're going to cover today is a brief overview. We're going to go into the form factor, the design ethos that went into creating this product, extrusion performance. Obviously, we're going to talk about the 3D printed heatsink because it's amazing. Accessibility, compatibility, and sensor options. So, for those of you that haven't seen this before, here are a few images of Roto itself. It's a super lightweight extruder, very compact, but still has enough force to work with all of the E3D ecosystem. A lot of usability has gone into the design, so making it as user-friendly as possible. And again, there is still a 3D printed heatsink. It's great.
Say that a few times.
Thanks, mate. So, some numbers. Roto comes in at 140 grams. Now, that might be a bit hard to conceptualize just as a number in itself. So for context, if you just take one X-axis motor from your printer, just the motor on itself, nothing else, it's half the weight of that. And that's including the heatsink, the gearbox, the motor, everything. So this thing is tiny. What does that mean? Well, that means that everyone around here, you're seeing printers that are moving faster and faster. But as you have more mass to move around, that job gets harder. So making it as light as possible means that you can push your existing motion system further than you have been able to before.
Cool. So we wanted to take people through a little bit of the way we approached designing Roto. And one of the big things for that was, as a design ethos, we don't want the extruder to ever be the limiting factor in your printer. So there are a few different things that might be why you can only print at a certain speed, a certain flow rate. One of those is how fast and how quickly can the hot end nozzle filament combination be melted. There comes a point where even if you push harder, you still can't melt any more plastic for a given hot end. So we want to make sure that Roto can always do that, and it can always deliver enough pushing power to be able to extrude for all the hot ends, that plastics, nozzle combinations. But we also don't want it to be too big. So what we did was we characterized loads of different hot ends with different filaments, all different nozzle sizes, and created this sort of data cloud of points. Axes kind of generalized and removed and stuff for secrets, but you get the idea. So to give you a line in the sand, this is where Hemera sits for its force output against flow rate. So as you can see, Hemera's always got enough extrusion force to be able to extrude at the maximum flow rate for a given hot end nozzle filament combination. But it also has arguably a bit too much in the sense that it has more than it needs, and as a result the system is heavier. This is our lighter weight Hemera, Hemera XS with a smaller motor. As you can see, the curve comes down and it gets a little bit more optimized, but it's still got some ways to go. This is where we've put Roto. So the reason that we can confidently say that it won't be the limiting factor is that these are the limits. Beyond this, it's not good printing, it's not usable printing. But Roto always sits with a force output just above what you can maximally get out of your hot end. Just for a bit of context, these are some other products on the market that we evaluated and tested. And as you can see, other people's extruders, sometimes they get smaller, and what that means is that they can't always achieve the maximum flow rate. So you'll think, oh, I'm not getting as much flow rate as I expected out of my nozzle, but it's actually not the nozzle that's the issue there. It's because you can't push hard enough. So that's what we optimized. To do that inside Roto, we've got 3 gearbox stages. We've got the initial planetary stage, which you can see down here, which goes into a secondary spur reduction stage. And then finally we have dual drive hobs, similar to what we had in Hemera. We've actually done some more optimization on those now. So the familiar 20-tooth gears that are in Hemera, they've actually gone down to 19-tooth gears with a bit of profile shift on them, and it actually means that they're more optimized, again, for, I guess, contact ratio, better drive transmission, etc. Total gear ratio, 11.262 to 1. We'd like to tell everyone about that as well. Also, there's a 3D printed heatsink. And then this TFR is something we've been using to evaluate things as well. This stands for torque to force ratio. And why that's important is because you don't actually care about the torque that you have at your final drive stage. What you care about is the amount of force that you're able to transmit into the filament. So if you kept your entire system the same, but doubled the diameter of your hobs, then the amount of force that you're then able to extrude with reduces. So there's a bit more information about torque to force ratio on our blog, and we've also got the data for other extruders on there if you want to have a look. But it's important to make sure that you're considering the force output of your extruder and not just a torque. One other thing that we did, which we're really happy with, is we've biased the system such that if you do have an issue with your print, if you get like a jam or something, which does happen and is unavoidable sometimes, then the motor's likely to stall. It's biased to stall as opposed to stripping the filament. I think we've all had to take an extruder apart to clean out a horrible, nasty jam where you've stripped all the filament and made a mess. And this is much cleaner as a solution because the motor just stalls, you pause your print, and then you can rectify that issue and then just carry on.
Cool. Yes, so back onto the 3D printed heatsink. So E3D's mission statement is to change the way that humanity manufactures goods. And we are doing that by trying to advance FDM as much as we can. But there are loads of awesome 3D printing technologies out there that are often underutilized for production. They're used a lot in prototypes or in one-offs, things like that. But what we have here is a SLM, so metal 3D printed heatsink. This isn't a printed mold that is then cast. The part is printed directly. It then goes through some post-processing in order to be able to add the threads and get the finish and things like that. But what that has been able to do is reduce the size and the weight even more. So the comparable machined heatsink that we were able to design, this version is a third lighter. It's also 4 millimeters shorter, and it is more thermally efficient. So it's smaller, lighter, and more performant. So we're super happy about that. And what does that mean? So that means, as you can see in the bottom here, we have some numbers about printing at higher ambient temperatures. Now, it's worth noting that that 40 degrees C is inclusive of PLA. So normally you go anywhere near 30 degrees and your heatsink starts to have a jam because you're getting heat creep, things like that. And we have really abused it when trying to do this testing. So we have a chamber where we put it in and we can control the temperature of it. And we then essentially get it to do lots of little towers. So it's lots of retractions. There's no filament moving through the system. It's trying to force a heat creep as much as you possibly can. And that was done for 24 hours with no issue. It just kept on chugging. This is with a bit of a safety factor in it as well, but this is what we're rating the system to. So this is our most thermally efficient heatsink, which just goes to show how awesome 3D printing is. And we, as a company, would just love to see it being used more and more in this industry and in every industry. So how have we done that? So there are A few advantages due to the design flexibilities of 3D printing. So the most obvious one is the skeletonized structure. So that's helped reduce the weight as well as enable to get the air flow through the system without creating a bit of back pressure for your fan. Additionally, the 360-degree heatsink fins. Now this will look very similar to a turned heatsink that you will get from like a V6 or a Revo Voron or something like that. And what that means is you are putting surface area and airflow all the way around your heat break. So you're getting the heat out from where the heat is entering your heatsink. Now, in traditional integrated extruders, you would have your fins off to one side or they'd be on the front. And so what that means is your heat has to go into a heatsink and then move through the heatsink. And so you're not actually getting the heat out as close to the heat break as you want. Then the third aspect is a new concept that we have come up with that we're calling the air brake. So with some of the air that's flowing through the system, it goes along the trajectory of that blue arrow. So it goes through the heatsink, curves around, and comes back underneath. And so what that does, that's only a very, very small amount of air. And that creates a little bit of a shield between your hot side and your heatsink, which means that it actually just prevents the hot air from getting into your heatsink. So when you're trying to optimize the thermal efficiency of your system, the most obvious one is like give it more surface area, give it more fan speed, things like that. But if you can just stop the heat getting in there, that also works. And so that in itself has really helped contribute to the numbers that I was going through on the previous slide. But no need for any concern. As I said, it's a very small amount of air, so it doesn't disturb any of your prints or your part cooling. It doesn't affect any of that. We've done a lot of testing to make sure. On usability, so what we have done here is we have a bistable idler mechanism. So this is a one-part assembly, and there is a flexure arm between the two parts of the idler. So what you do is you click it over to the left, and that will disengage the hobs from your filament, which means you can then load your filament in and out with one hand. You don't have to be there prising on your extruder to fight against the spring force. It's just there. And then to get it unlocked, you then pinch the two items together, and then it just pings back over and re-engages, and you're good to go. And in terms of the longevity, because as soon as you start putting flexion items, the first thing is how long will it last? Well, it outlasted the test rig. It broke the test rig. So it got to 16,000 cycles, which is a stupid number. It equates to a filament change every day for 43.2 years or something like that. So it's going to last. Don't worry about that. And then similarly, on mounting options. Now, mounting is always quite a tricky design aspect because there isn't a standardized way of doing it. Every carriage is different, every printer design is different, and so traditionally on an extruder you either have threads or you have holes, and that's it. You are stuck with putting screws in or screws out. So what we have two holes on either side, but they're sized the tapping size for an M4, which means that you can either use an M3 straight through, you can tap to an M4, and we're also going to provide some polyfix self-tapping screws for those that don't have a tap at home, and for anyone that's had some of the original E3D products and says we put wood screws in, now I promise you they are plastic screws, that's what they're meant to be used for. But yeah, so this gives a lot of flexibility so that you can hopefully try and integrate it as seamlessly as possible into your system.
In terms of hot side compatibility and what you can attach to the business end, the obvious one is the entire Revo ecosystem screws right in. It's got the feature for the spring, for the heater core. You can screw in all of your Revo nozzles, but also through using the Hemera heat brake, you can screw in one of those. That gives you an M6 out, so you can put something else if you've got a specific application. If you've got an older E3D product, it's going to work with all those as well. And then in terms of some of the other stuff that is an optional extra, we have a filament presence sensor up at the top. It's currently, well, I want to use the laser pointer. Oh no, it's not working. Excellent. There's a filament sensor on the top, which has an LED for status, and it also has a little action button which functions like an end stop, so you can program your machine to run macros like preheating your bed or unloading or reloading some filament. We have a 3-wire tacho fan option. We have a heatsink thermistor, which is embedded right down next to the heat spreader where that connects. So that as well as monitoring whether your fan is spinning, you can also check that your heatsink isn't getting too hot and make sure you don't get heat creep. And we've also worked with a couple of partners, Duet 3D and also LDO, to create some specific Roto toolboards, one for Clipper firmware, one for RepRap firmware. They have mounting features, so they mount directly into the same two mounting holes. So yeah, that's a fairly brief introduction into Roto. If anyone has any more questions, please grab one of us or anyone else at the E3D stand. Like, we'd love to talk about it more, as you can tell. So yeah, thanks very much.
Thank you.
Thank you guys very much. Yeah, very well-deserved round of applause for these guys. Yeah, really appreciate it. Well presented, and as I said, if you want to ask any more questions, over to the E3D stand.
Right, hello everybody. Just before we go on to our next speaker in a little bit, I just want to make sure that everyone's got... hello?
recently teamed up with E3D to bring you the most extreme of nozzle solutions, which is the Revo Diamondback. It's just on the market recently, but Diamondback have been making polycrystalline diamond nozzles for a good few years now, and in general have been making these products in the industry for 40 years. They also were the sponsors of the party last night, so we were all dancing, thinking and dreaming about diamonds, so thank you guys very much for that. Anyway, without further ado, over to you.
Thanks, Josh. All right, so we have a common theme going around here at the show, and that is people are losing their voices, and my co-presenter, Mark Marzitsky, is no exception to that. But he completely lost his voice, so he will not be joining us today. He's a great guy. When you get a chance to, cross paths with him, maybe at other shows later on, get to know him. He's a great guy. So we're very excited to be here at the very first Smurf Sanjay Mortimer RepRap Festival. However, we as a Diamondback Nozzle team never had the opportunity to meet Sanjay in person. However, we've had the opportunity and blessing to meet many of his friends. And there's a famous proverb that reads, a man is known by the company he keeps. And so in our experience, Sanjay must have been a very beautiful person because all of the friends that we've met have been just wonderful to us. We're new in this industry, relatively new in this industry as a company, and we've just been accepted and with such a warm welcome, and we appreciate that. But as we're here in England today, figured we'd give you a proper introduction to who we are as Diamondback and who we're a part of as a company. It gets a little confusing here because we've got Diamondback, US Synthetic, and Champion X. So to clarify that a little bit, US Synthetic is the company backing Diamondback, who owns the technology to produce the diamond. US Synthetic is based out of the West in the United States. We're in the state of Utah. And US Synthetic is owned by Champion X out of Texas. So US Synthetic has been in the business for over 40 years, producing premium diamond products. And that's no exception to now the nozzles that we're producing for 3D printing and additive manufacturing. On the screen, you'll see a picture of our facility. We've got 3 separate buildings on the campus, and all of the manufacturing of the diamond and all the manufacturing of the nozzles is done there in Utah and on site. We keep that manufacturing close to us, and we're able to make sure we maintain that high premium quality that we're known for in other industries as well as now in 3D printing. So a little more about diamond here, right? So all of us are very familiar with the single crystal diamonds that's used in jewelry that were produced by the Earth. The Earth has created perfect conditions to make that diamond. A lot of heat and a lot of pressure. But also included in that is thousands and thousands of years for those to form and be produced. Another on the screen here, we got also a picture of coal. So why would we throw up coal up here? Well, coal's got the base atomic features as well as diamond. Well, what's the difference here? The difference of the processes that it's been through, that heat and pressure to convert that same atomic base. Our facility in Utah that we just had on the screen there, what we will do is we'll replicate those conditions that exist down in the Earth with immense pressure, immense heat. However, instead of thousands of years, we can do it in 10 minutes. So we'll take diamond grit and convert it into the solid structure that we're using in the nozzles. So that's what we want to go through here in the next few slides here is just how do we make this diamond? How do we go from diamond grit into a solid structure that can actually be used in a nozzle? We've got a little animation coming up here, and I'll just kind of talk us through that a little bit. So this process is called diamond sintering. So we're not putting diamond in, say, a glue or a matrix, but we're rather creating diamond-to-diamond bonds in this solid structure. So here we go. We take that diamond powder and we'll put it in a refractory metal. That's a high melt point metal because of the conditions that it's going to go into. We'll add tungsten carbide into the backing of that diamond. And I'll explain that here in a moment why. We put it in an assembly with a heater, a graphite heater, and some gasketing material. We're going to have atmospheric pressure and then immense pressure inside this press that you see on the screen. It's hydraulically ran, mechanically ran, And so these anvils will come in, apply the pressure, and then we'll run a current through this assembly. If there's a graphite heater around the diamond, and this will go over 1400 degrees Celsius during the process. Again, that's why we have to use those refractory metals that aren't just going to melt during the sintering process. So we have the base layer of diamond, and then as I said, we put a tungsten carbide piece in there, and it has cobalt metal in that tungsten carbide. Well, that cobalt metal will melt and infiltrate into the diamond powder, and that's what allows the magic to happen. It's a catalyst for that diamond to diamond growth to actually occur. So without the tungsten carbide, we'd have to change the pressures, change the times and all that, so it's kind of somewhat the secret sauce to make it happen. So we take the diamond grip, we take the substrate, put it in the press, and we got nozzles, right? If it was only that easy. The conditions that go in the press are really unique, very interesting. As I said, you've got atmospheric pressure, and then it's over 12 gigapascals, or 1 million psi. It's hard to even comprehend what that means, and so we had a calculation here made, and what it is like taking the Eiffel Tower, flipping it over, and putting the tip of it in the palm of your hand. The pressure that you would experience there is the pressure that the diamond experiences going through the press. I still don't understand it, even with that explanation. So, now that we have the diamond made, the question is, why would we put that in a nozzle for 3D printing? Doesn't it seem a little extreme, a little excessive? Let's talk about that a little bit here. So, we got a video clip here I want to show you. Some of you may have seen it before. We have it. It's been out on YouTube and things like that. But it's not a scientific test that I'm going to show you, okay? It was a Friday afternoon. A few of us said, hey, let's go down to the shop and have some fun. So we took some competitor nozzles that were out there, and we went to town with a grinder. So I want to show that to you here. Start out with your common brass nozzle. Nothing too unexpected there, right? Move on to something a little harder, steel nozzle that we use for abrasives. Full disclosure, all of these videos are 2 times. They've been doubled up, but all of them equal. We apologize to E3D already. Now tungsten's a good material. As I said, we use tungsten carbide in our process. So you can still see we have some wear here on this accelerated test. You can see we're working up here in hardness. The ruby just fell out, wasn't retained in the nozzle. And last we ran with the Diamondback. No trickery here. This is, again, just going down playing. Look at the tip. You could go and throw that in a printer and start printing. So, okay, so we had some fun here, but what does that highlight? That's highlighting one of the key properties of diamond that we're all familiar with, and that's the hardness, right? That with a diamond tip nozzle, you can print whatever filament you want. It can be the carbon fiber-based nylons, anything with glow in the dark, but also you can just print your plain PLA, so it's kind of your one-stop nozzle. It's not specific to those abrasives necessarily. On top of that, you know, in the more extreme filaments, such as your ceramic-based or metal-based filaments, you're not going to experience wear, again, due to this hardness factor that diamond has. Why else would you want to put it in a printer? We've got some of these other properties we want to highlight here, and that's the coefficient of friction. Not many people are aware that diamond on diamond has a lower coefficient of friction than Teflon. We actually have a sister company that produces diamond bearings. We take that same diamond, polycrystalline diamond, put it in a circular array, and that diamond on diamond has such a low friction, we don't even grease it or lubricate it with anything. They work in very harsh applications that take high loads, high compressive loads, and places where you don't want individuals have to go in to replace or repair those bearings. A couple other properties just to highlight. So many here at the show probably walked by our booth and saw the ice sculpture that we have. That's not just for show, it's for you to come and experience. So if you haven't done so, come experience the thermal properties, the thermal conductivity of diamond relative to these other materials. it far outshines any other material that's out there that are being used for nozzles in 3D printing. And just a fun fact is the thermal expansion is that diamond has a low thermal expansion. So as you vary from maybe your lower 200 degrees Celsius up to 300 degrees Celsius, you're not going to have variation in the orifice independent of what you're printing there. So continuing on, as I said, we pride ourselves in being the premium leader in diamond products. We're not new to this. We've been around for 40 years making these products. This is just highlighting some of those products that we produce. I just mentioned the bearings application there you can see at the bottom. Those will go into applications in such as wastewater treatment where people are not wanting to go in and change those. And we've got PCD drill bits. So people come to us and they'll say, hey, this is diamond, it's just going to break. It's not, I mean, it is a brittle material, but you're not going to break it. The same diamond used in those drill bits to drill into the earth is the same diamond that's going into the nozzles that we're producing. Another fun one we like to highlight are these hydrokinetic power generators. So they'll put these bearings down in these electric generators that are in maybe a river in remote areas of the world, and it will be the power source for some of these remote villages and towns. It's a fun application that one of our products has gone into. So, I guess the last question is, what benefits can you expect? We talked about why put it in a nozzle, so what are the actual benefits you would see from running a Diamondback nozzle in your printer? There's a little video clip again highlighting those. We'll take you inside the Diamondback for a minute. So as we mentioned, a tip is solid diamond. It's not a coating. It's not going to wear out. We actually polish the tip of the surface to a mirror polish finish. So you're going to get ironing as you're printing, essentially for free, if you will. Internally, the geometry we designed, along with that low coefficient of friction, you're going to reduce clogging, reduce the extrusion force required, and again, with the thermal properties, have a consistent output, consistent print when using diamond. The top bullet point we have there is print any filament. And a lot of us might think, okay, I'm going to go print that harsh stuff. I'm going to print that carbon fiber. But we've had some customers come back to us and say, hey, we just want to give you some information and let you know. There was some TPU, some softer TPU that I wasn't able to print before, that now I can with the Diamondback. And again, goes back to that low coefficient of friction, goes back to that lower extrusion force required to make the print. So that's been fun to receive the feedback from you, feedback from the community of what you've been able to do with the Diamondback. As I mentioned, unmatched wear resistant because it is solid diamond, it's not a coating. The improved layer adhesion is due to the fact that thermal property. If you think about your extruder end system, you've got a heater up above the nozzle, the thermistor that's away from the tip measuring what the system temperature is at, and there's a thermal gradient between that measurement and where the tip is. Because of those thermal properties, you can rest assured that the tip is at what the system is reading. And as energy is pulled out, as filaments extruded, that energy can be replaced and temperature maintained and not be varying depending on speeds and different accelerations and velocities. Along with the low coefficient of friction, it makes it easier to clean. If you get some buildup of filament on there, a simple wipe and it will come off. Again, it doesn't want to stick to that diamond due to that material property that it has. Lower operating temperature, again, just goes back to the thermal property that it has. You most likely do a drop-in replacement. The housing is brass, primarily for that purpose, so that it's a drop-in replacement so you can maintain your base slicer settings. But if you run a temperature tower, you may see that you can actually lower temperatures rather than have to increase them. And that differential, you'll see increase as you get to the higher temperature filaments. So that means less wear and tear on your system, on your printer. You're not having to run as much current through that heater, less energy consumed, and just a wider band of filaments that you can then print with your specific printer. Lastly, I just have there is that diamond is made in the USA. Again, we pride ourselves in being the leader in diamond products in all markets that we're involved in. And again, this is no exception here with the additive manufacturing and 3D printing. I kind of want to wrap up here and share with you, this was a marketing video put together by E3D. They did such a great job on it. It was about a month ago that we announced the collaboration, as Josh mentioned, of the Revo Diamondback launch. So let me share this with you. This is the video that they put together, and I thought they did an excellent job. So again, we appreciate E3D for putting that together for us. We're excited to announce here at the show that beyond the Revo, E3D will now be bringing all Diamondback products to the European market and making that available. So that'll be forthcoming here in the next few weeks, next month. So you can look for that and see. And we appreciate your time. Feel free to stop by the booth if you're here on site at the show. Come check out, again, the ice sculpture. And if you have any questions, just let us know. Thank you for your time.
for a university. The work that Andy does on FullControl is really very exciting. He solves problems that you didn't even know that you had with solutions that you could barely fathom existed. So yes, up next I'm very excited to welcome Andy to talk about the software that has supported him and his research students to author 82 research publications, secure multi-million-pound research funding, and most importantly, create weird and wonderful print paths for pretty Instagram posts. Andy, over to you.
This is my clicker, right?
Yeah, it's your clicker. Open it up again.
No worries. Okay. Hi, everyone. Thank you for coming and listening to my talk. So, yeah, I'm going to talk about FullControl, mostly just using loads and loads of videos that I've made for social media that really kind of convey a lot of different stuff that I've done with it. I will go into some detail about the research stuff later if I got time, but really I'm just going to give you a snippet of that. Anyone super interested in that can come and talk to me afterwards. So, first, just a little bit about me. I like barbecues, and I have some kids. I kind of like them as well. The barbecue there is actually a wooden branch from behind my garden that I bolted on. Everybody told me it wouldn't work, it would be burned down, but it didn't, just like FullControl. And this Belgian beer, there was the croaky voice is mostly due to talking too much yesterday, big clues. But there was also some Belgian beer involved. Then football, I love it. And then with research and stuff, I started a PhD at University of Leicester. That was mechanical properties of biodegradable polymers. And then I moved to Nottingham and did research. And I started with custom G-code for 3D printers from basically the very first time I used one. And then I was doing this G-code and I started doing some weirdy mathsy things. And then I figured one day to do some like artistic pieces for Instagram. And it's kind of taken off from there. So there's a lot of social media things showing that. What we actually use it for is often very boring things, just lines, measuring their width and things. But I'll get into that. So if you want to talk to me about any of these things instead of FullControl, that's completely fine as well. So this is basically what I'm going to talk about. A very brief background, talking what sort of process I'm talking about, why I did FullControl, and then loads and loads of videos. Finally, maybe the mechanical properties. So this is basically what we're talking about. We've got a filament or some kind of materials coming in, we're melting and extruding. Lots of you'll be aware, just for those aren't. And then from that nozzle, we're moving around. In this case, we're printing a porous nose for tissue engineering. So we're growing cartilage tissue in that nose. And then when the cells grow and the tissue forms, the biodegradable polymer disappears. So PLA, really rubbish polymer. Everybody hates it for 3D printing, but in the medical field, it's a beautiful polymer that we've been using for decades and is really, really well respected. So that's kind of what we're talking about. And the typical approach, you'll know, we get the model, slice it into layers, and then each layer we get the print path, print it, test it, do whatever. And then we come back and we'll revise either the model to try and get our slicer to do what we want. We'll try and change the slicer settings to get that. And that will come up with our new model, print that, blah, 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 blah. With FullControl, though, we do it slightly different. I'm going to introduce some of the sort of annoyances I got early on that justified me creating custom toolpaths and then go into it. So this was some tissue engineering scaffold again. You can see the blocked pores. That's because the nozzle was moving to the end, moving across, moving to the end, moving across, moving down. And as it went round that corner, it kind of pulled the material in. It was slowing down and extruding. This was a super elasticy material, PCL. It was a bioprinter that cost 250K, so it was absolutely awful at printing, of course, and it just couldn't do retraction or anything like this. So looking at it, we couldn't really change the material or the printer, but we could change the print path and just did this tiny change. Coming to the end, just nudged outside, move across, go to the other end, nudge outside, go across. And what that meant was our defect got moved to the outside. Didn't care about the outside at all. We wanted nice, neat pores on the inside. So that was a kind of really simple little tweak, but I couldn't do that with the software that the printer came with. And then another example, got one of my project students to do a kind of stress test for 3D printers. And I was not really aware of slices much at that point. I was just trying to get what's the smallest thing I can print. And this is a nice example. They were printing with the settings with a line with 0.4. For a 0.4 wide little cylinder tube, it printed perfectly. But when we went to 0.6, it came up with this mess. And I was like, what's happening here? Looked at the print path, and it looked like this. It was kind of printing one circle, and then it had half left. So it put in little bits to try and figure out the other half. Doesn't make sense, but slicers aren't designed for doing these weird, tiny little things. So that's not saying slicers are rubbish. It's just when I was looking at thinking, we can just print this wide. That's what we just need to say to do. So then I kept on going down that route. With custom print paths, we then skipped that whole CAD model, STL, slicing, and print path for each layer, and just designed the print path right from the beginning into G-code. Actually, now I skip even that step, and we can design the print path and go straight to the manufacturing and do things like robot printing as well. So we keep on going. And when we do feedback, when we've got some problems and we want to change our settings to get better quality, before there was loads of different errors coming in at different stages. It's quite hard to fix them. Whereas when you just come back and there's just a single step, it's much easier to diagnose and correct those failures. So that's the kind of principles of it. And designing every single point is kind of difficult and annoying. So then I realized that maths could be quite useful for this. So this spiral here, just like vars mode for normal 3D printing, it's basically x is cos of t times 2 pi, y is sine of t times 2 pi, and then you just take t to go from 0, 0.1, 0.2, up to 1. And then set z just to go up with t. So z is going to go 0, 0.1, 0.2. And that gives you that spiral. And then you can print it by just splitting that up into lots of points. So I can write those 3 tiny little equations and get out of it 100,000 points. And it's really, really condensed. So that's used quite a lot in FullControl, and the thing I'm really working on is trying to make sure that's sort of hidden away. So you don't necessarily need to think about cos and sine. You can just think about a helix and say, give me a helix, and I do the rest. So now, loads and loads of videos. So first off, this is a phone holder, and a lot of these are showing something interesting, but actually I'm testing quite a lot of secret things. So here, I was testing this really nice lattice structure, which was printed with 0 travel and really relevant to things like anatomically matched braces and stuff. And I was also testing the resilience of a print path to changes. So all different users were putting in their phone dimensions, and it was printing, and they were saying, oh, I printed perfect, really fast, really good. And it just worked really well and gave me confidence that actually a single print path could translate to all different printers and different subtle changes to size to get this really nice design. This is showing the actual website. The users would just go in, tweak those settings, regenerate the model, and then just simply click download G-code. So the original version of FullControl was all you define every point. This is like the opposite, and it's just then saying that you don't need to do any of that. You just choose your parameters and you get it. These are actually the first ones that I programmed, these like mathsy wavy things, just like those helix. And I was actually programming these during one of the Super Bowls. And this was, I think, one of my, if not my first ever post. And I just realized all this beautiful geometry was coming so simple because the whole equation for this was in one row in Excel. And it was just really tiny and fully parametric. And I just couldn't believe that this actually came out of FullControl. I was like, wow, this is nuts. And then I moved from there towards things like the phone holder, as you still. More recently, taking that to a new level, these are all variants of a lampshade that comes out like that. So you can go to the website, tweak some settings, and you can just print it. And like with the phone holder, it's the same print path, but every single one of them in my mind. They're all different, but it's doing exactly the same thing. There's not like 3 lines instead of 2 at any one point. It's always the same. So it prints basically perfectly whether you change any of these, as long as you're not going to like crazy overhangs or something. This is moving on to some of the more weird things. So that's with the non-planar print path. You can see all of the layer lines are nicely matched to this geometry. And this was called going to this massive robot, or not robot, it's a gantry printer. And that was just a really nice first explore into kind of matching the layers to different heights. So kind of like Arachne, where you're doing different widths along the XY direction. This is doing the same in Z direction. We have a research paper on an equivalent to Arachne that we did before Arachne, by the way. So talk to me in there if you want to see that. And that was really interesting to get a feel for what kind of challenges there were. You saw that weird long nozzle. That kind of overcame but it's just my first forage into it. This more recently is moving on to a robot. So now we've stuck a Chimera with a supervolcano on a robot. And this is just showing my very first attempt at some weird Pringle-shaped thing. And going on this, thank you to Brendan here, doing this awesome, whatever you call this, upside down printing tube thing with this super neat little 5-axis stage. So this again is showing, I didn't really do anything with him. He just took my design and generated it and tweaked it to make it work. So it was a nice thing to see that that could actually go. And people just loved this. It was going all over the internet. And it's just creating impossible geometries. And you can look at it, who cares about some stupid S-shaped tube? But it's actually really relevant to certain applications, especially moving from polymer to, say, metal printing, ducting, and airflow devices, rocket engines and things are what people are really talking about, where this kind of printing with different shapes but not having a weird layer. Like, you couldn't do that with a normal layer cutting. It just doesn't make sense at all. And very recently, in the last like 3-4 weeks, with Tony at Duet, we decided to make a 4-axis printer that's supposed to be as super easy to use, easy to produce as possible. Because I think 5-axis is really difficult and challenging to design for. All of my stuff is basically ultra design for additive manufacturing. It's kind of thinking, what can I do with this thing, and now design for that. And with 5-axis, it becomes quite tricky to think, okay, which way are we going to move, and then we're going to collide, and all these things. Whereas 4-axis makes it a lot simpler. This is obviously just a stupid example part, but there's quite a few applications where I've had access to a robot or a 5-axis printer and genuinely preferred to go down a 4-axis route because it just makes the toolpath, not the toolpath design, but the actual like hardware considerations much simpler. With a robot, if you start just moving around and you're only hinging in this direction, it just works all the time. If you start rotating, now my wrist is going to the limit of what I can do. A robot's exactly the same. So now I've got to consider how far I'm twisting. Whereas if I just do this hinge, it's really much simpler. So that's where this is supposed to hopefully get that 4-axis step towards 5-axis. And what I really want is for people to kind of test this, get non-planar slicing working with 4-axis, and then go from there to 5 and stuff. This was with my mate in Madrid, and he got some new milling machine, and he was like, let's play with it. And it was just beautiful. We created this design with FullControl in like 10 minutes and then started printing it. And it was really interesting to see how the considerations are different with machining and printing. And actually quite a lot simpler with machining because you don't need to have sort of a start and finish the same way as you do with a line of polymer. So we do things that are not just extrusion additive manufacturing. We do concrete 3D printing and machining of the concrete. We do inspection, probing parts to get data, microscopy on printed parts and things. So it's not just toolpath design, it's manufacturing procedure design. And then now sort of moving on to new concepts for print paths, I'd say. And I say new, I'm sure other people will have done these before, but I'm trying to put them all together and see what you could do with them in terms of designing different kind of geometries might be suitable for this type of toolpath. This geometry might be suitable for that kind of toolpath. So this is doing what I call snake mode. It's like vase mode, but instead of going all the way around and gradually moving up, you just go across, up, back, up, across. So it's kind of printing this whole thing in one continuous path, which means I can print it one wall thick instead of having to do two, and has these various advantages in terms of being simpler to design. That was a soap dish, but it could work for anything. Basically like a C-shaped vase instead of a closed vase. This would be the vase mode equivalent. This is showing then varying extrusion width, so like with Arachne, but this is single wall, and varying with continuous changes to speed so that the actual extrusion flow rate is constant, which is really important for things like concrete printing, difficult materials and Bowden printers, where just changing speed means you get different widths and you don't need to worry about changing the actual flow rate. And this is obviously kind of visually aesthetic, but we've done exactly the same kind of thing for prosthetics, where we're changing the thickness at different bits, and now at the medical braces. And that's, again, going back to my tissue engineering side of using the continuously varying extrusion width to get graded lattices. All of those ones on screen were exactly the same print path, just varying extrusion width whilst we're printing that print path. And this, I've got a model on my FullControl GCode, which is doing the ASTM specimen, just like that flowing, streamlined thing you just saw there. This is sort of random meshes, really good for, we have applications that are about filtering and biomedical things where random pores are kind of interesting. This one's not random, it's kind of deliberate, but that way of printing with just strings in a controlled manner is kind of interesting. It has some sort of applications. It's a good example of where you really need to just design the print path, because each line you're printing is the geometry that you want. There's no point in creating a CAD model for that to get the print path, because it's just the same thing. Really weird blobs. So these are just, again, mostly just exploring what's possible. How wide can we go? And these are going to literally 10 times the diameter of the nozzle, which is interesting in terms of it being completely solid as well. So you could get some interesting mechanical properties. What was the other? There was something else I wanted to talk about with this one. I can't remember now. Maybe it'll come back to me. But so that's potentially there as just an aesthetic tool, but also just exploring what is possible in terms of melt flow rates and stuff. This is a good way to test how fast can you literally extrude material and maintain a good structure. That's the nozzle size you see with those things. So that width from that nozzle. And I'm sorry for this logo every single time. It's because I've just taken these I've created these individually and put them together. This was a cool one thing. Okay, overhangs are seen as a real difficult thing. And actually, if you have a really nice tool path that just lets the filament ooze out and it sticks there, just wants to stay there, touching its neighboring filament, then you can get that to work really beautifully. And you get great, like perfect quality. And there's not great mechanical properties there maybe because it's just touching, but as a first layer, it's beautiful. Then you can get nice squished layers on top of it. So that's kind of a completely different design rule, where now if you want to do symmetrical overhangs, that's completely fine. But that doesn't exist as a design rule for normal additive manufacturing. So there's design rules that are kind of generic, and then there are design rules that are thinking about the toolpath, and they are massively, massively different. So for that one, having it kind of the same overhang distance everywhere means you can do it with the same number of filaments everywhere, which is really convenient. So that would be something you'd look at designing, thinking, if I can do it the same like step over this side as that side, that's what I should do if I can. This was showing where you can't always do multi-axis. So this, as it's going up, it's going in and in and in, and then eventually goes down. So the overhang is at minus 30 degrees or 120 degrees. And you couldn't get a nozzle in normal to the direction of printing because it would be just now pointing up through the existing part. So here the only option is 3-axis, but you can still get this kind of geometry if you design a really nice, smooth, varying toolpath. And this looks kind of weird, but is very similar in geometry to what you might get from any medical braces and stuff, where it's kind of morphing in height direction and width and stuff. And it just tiny tweak from that to a medical device, but you still get the same benefits as what I'm showing there for that. The pin support challenge, again, mostly this was to show the ability to print these vertical struts, but also printing kind of horizontally from them. It was again saying that this is, when you think about what the process can do and design for the process, you can do things that you just never have thought possible. So this, could we use these vertical struts for printing things like stents? But the other thing they could be used for is like support. So we print a vertical support in your slicer, and then you potentially save quite a lot of material. This is moving on towards process calibration. So this ends up with a really beautiful object, but what I was actually doing was testing, as I gradually change some parameters, what happens to my structure, because I wanted this really neat spaghetti-like pattern, or really random spaghetti-like pattern, like you're seeing now. Well, not quite now. It's about now. So that's when I was going through these settings and figuring out, okay, that's actually pretty cool as well, and getting this map of what types of geometries I can get. So that's every single layer, slightly different, gives me this really quick understanding of what parameters are good to get something. That, in this case, it's kind of a weird spaghetti-like structure, but we've also done this for seeing what's the maximum width we can print, what's the maximum flow rate, all things that kind of researchy and boring. This is taking that to the extreme then, where I'm taking a 2,000 different unique combinations of printing parameters, and they're printed in less than an hour. And it's all structured so you can do direct comparisons side to side, and a really quick kind of examination. If you had a microscope, it'd be super quick. On the tool changer, just go bam, 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 and get all, what's it called, images that are exactly registered in the same location. So this was, as I say, mostly just to show the idea of really mass numbers of parameters in a single well-designed test. This could then translate to other things like testing the maximum extrusion width and stuff, where you get these different temperatures, what the maximum extrusion width is at different temperatures, different layer heights, whatever. And this one is actually directly linked to Sanjay. So when I visited E3D a few years ago, and he was talking about the Hemera, saying, oh, this is super responsive, it's much, much better than what they've currently got. And we were testing it versus some existing extruders and Bowden extruders to say, I'm going to go through this video again, by the way, to say how quickly does it react? If we tell it to extrude more material, how long does it take before it actually achieves more material? So we printed really nice aligned lines, and then we knew the start point of when we changed something, like change speed, or told it to print double the line width. So we could then go with a microscope, and with the toolpath, designing a microscope moving across it, and get this kind of video. So what you're actually seeing here is that middle one and the bottom one are Bowden, and the top one, it has a very slight pinch when we double speed, because it's slightly under extruding, but then it just recovers instantly. The other ones take ages to recover, 50 times the nozzle diameter, just because that Bowden takes a while for the pressure to build up. But that's not the end of the world. I'm not saying Bowden is completely rubbish. It's just that if you're going to use them, you have to factor that in. And in some of the cases, that might be kind of useful if you want it to be kind of more sluggish in response. If you don't want visual defects, for example, a very slow change, you won't notice it visually. And really, I just chucked this in because some guys used FullControl to make this weird Christmas tree. And what I really love about this is he's taken my Python like template model, and he's created his own one and put it there so other people can go and download that model and just do it. And I saw somebody else had printed it and it worked perfectly first time, they said. And that's the extent of the model for that. That's like your CAD model, your STL, your slicer settings, everything in that little bit of code there. And you can see the preview of the toolpath at the top left. So the idea with that Colab Python thing, you don't need to install any software. You just go to the website, you need a Google, you log in with a Google account, but then you just run these cells or press Control F9 and they'll all run, and you'll get the preview, you'll get your G-code downloaded, you just choose your printer. So it's a really easy route into using Python without necessarily knowing any Python or installing it. Okay, so that's a nice range of stuff that I've done with it. I'm going to talk a bit about research and a bit about how FullControl actually works. So the mechanical properties stuff is basically what I have been doing. My main thing has been studying interlayer bond strength for the last kind of five years. I've had several PhD students and a lot of publications on it. And yeah, we were most interested in this weakest aspect, trying to improve that interlayer bit. And this was what we started with, tensile testing of this specimens printed with a normal print path. You can see quite a few things going on, but that pink bit is actually the contacted area between each layer. So the strength is basically just depends on how much is contacted there. All the bits that are darker, they're just with air in between them and the next layer, so they can't transfer any force. I was looking at it, and that's a complete mess. It's got a weird blob at the top. It's got a thinner contact area, then wider, 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 wider. This diagonal line is when the nozzle moved from the end of one layer to the beginning of the next. So the whole geometry that's affecting, critically dictating your mechanical properties, is kind of this weird accidental result of various accelerations and stuff. So we said, let's just simplify this. What we actually want is something where the green area is what we're studying. That's what the best case would be. And we simplified it to just look at a single filament and really understand then what is going on. And this is how we print it. A really simple box. Takes like half an hour, and we get actually 24 specimens out of that in the end. This only shows 8, but we now get 6 out of each side. It's tapered the extrusion width, as I showed in some of those videos. Really simple to design that. So we get a dog bone effect because it's wider at the top than the bottom, even though we're cutting out with just razor blades. Avoids having to have some weird dog bone shaped die, which then is a nightmare because you've got a specimen stuck in a dog bone die. And that's the result. So that fracture surface is just perfect. And you can see all the little details, like at the edges, slightly different mottling color. We can see it starts at one end and ends at the other, and just gets so much detail and repeatability. And then we can measure that area really easily. This is quite a hard area to measure. That's super easy. And this is then testing the mechanical strength in the filament direction, which is basically bulk material strength, and then across the interlayer. And it looks like your filament strength is much, much higher than this. But actually, when you look at it in more detail, I think that's the actual area that is sustaining the load. And what is that? It's 25% narrower. If you imagine this, that stick's going to be massively easier to snap. And you'd expect the force to be 25% less, and it actually is. So in fact, they're both just the same strength. The only issue is one of them's got all these grooves in the side, which is kind of like taking a sheet of acrylic and just scoring it 1,000,000 times with a knife. Of course, it's going to be much, much weaker. So we tested this with all these different geometries, all printed from the same nozzle size, different printers, and basically found this to be very consistent. I'd say about half the materials we ever test are showing bulk material strength. We've tested it across all different temperatures, layer times, and various things. So we have quite a lot of data to say that this is actually true. So that stuff, I got 1 million publications that would be, I can go into lots of detail with carbon fiber, different materials, and all sorts. So if that's interesting, come and chat. And then finally, I'm going to whack through a few of these. This is, as I said, the stents model that we were seeing printed at the beginning. That's for references what research is currently doing for stents. And those stent diameters are far, far bigger than what we're talking about in this model. So what we're doing is just printing vertically, just like the pin support challenge, to get those. And this was a lot of process calibration, printing lots of struts to find out how to do them best. That's what you're seeing here, doing them at different angles, trying to get that really clean break from the top of the extrusion to that end. And that's on an Ender 3 we didn't optimize temperature. It was the first PLA we tried. The guy got this nozzle made, that was it. We're not like doing anything complicated there. It's just a really simple path, thinking about how to actually get this kind of structure. And that side of, there's loads of related research going on in my group, the group I'm in, on things like FEA. So a lot of the stuff we're talking about does link into quite some interesting different bits of research like material property, material development and stuff that I'm not really talking about, just for reference. And then this is printing tiny little strings, which we used for drug diffusion. The cross-sectional area of them was so tiny compared to the surface area that we were getting orders of magnitude increase in drug release rate. There's various other things that you might do with these strings. We were just today talking about creating porous structures with them for filters. This is printing metal. We're designing this print path. It's an awkward print path. We can't do it with one continuous pass. So we're doing this weird thing where it's kind of takes 3 or 4 layers before we've actually completed a cycle of printing, and we start back where we end back where we started. So it's rather than designing 1 layer, we're designing 4 layers and then repeating, and then we get this really consistent path. When we tried this without using this approach, it was just a complete mess. This is a difficult material and really tiny sizes. So I'm not going to go into detail, but Excel design software began with this tissue engineering collaboration. I created an Excel sheet for just this design. And then I gradually thought for my other students, they wanted something that was not design specific, that had these basic features like a line, a circle and whatnot. And they could then assemble them to do a overall whatever. Like all of about half the videos were using the Excel version. And that's a journal paper that's open source, I'm pretty sure, and if not, it's on ResearchGate that you can download. It really goes over a lot of the research that we've done. And then with the Python version, it's on a GitHub website. You can go there, go to this is one of the examples. There's a gist. If you go to this website, you'll be able to use the design template to create your own designs. I've got a couple of videos on there that explain it, but it's not quite super easy to use at the moment. I'm going to work towards that. At the moment, it's kind of good if you have a bit of Python knowledge, but we're working towards making it then really friendly in terms of getting started. So that's just kind of gradually coming. This, I think I've talked about. That's it, really. So a lot of this research, I've been technically involved. Really, I try to be massively technically involved in everything, but there have been a huge number of people that have put the things together, especially for the research side of things. And especially thanks like Dirk Lias, when I had the open source Excel version, he kind of said, I really like, I want to help people, industrial designers, really be able to design things with robots, manufacturing plants and things that is overly complicated at the moment. And he knew about software kind of structures and architectures and came to me and said, let's go down this more professional route, easier for people to contribute and stuff, and that really stepped us from Excel towards Python. And all the website and everything, how I programmed that, so I personally created all of these things with his guidance, and it just would not have happened without him offering masses of time for just out of his own interest. The rest of them are generally for research, and then of course Sanjay gave me a tool changer right back in the day and got me started on a lot of my inspection stuff, and Tony's been great supporting the actual 5-axis development and things, giving us tips on how to get the firmware working, and again helping us with hardware. So thank you all for your attention. I don't know if we have questions or anything, or if not, I'll be at the stand through there towards the end in the middle.
Thank you very much, Andy. Really brilliant, really. Thank you very much. Unfortunately, no time for questions right now because we have Baki from Zax who will be coming up right away, but feel free to go and find Andy on his stand and quiz him. He hates talking about FullControl.
Good afternoon, everybody. I'm Phil Bateman from E3D, and I've got the privilege of introducing to you now, next up on stage, is Baki Gezgan of Zack's 3D printing technologies, who intensely refine the perception of additive manufacturing industry. Let's find out more about Zack's, how it's come to the powerhouse it is today, and give a very warm welcome to Baki.
Thank you. Hello, everyone. So I would like to tell about our company's story, so how we found it, and what's my background and our team. So the first thing is that, so I'm not an engineer, I'm a molecular biologist. So, and I love to design FTV planes and 3D printer manufacturer, and also Zack's a founder. Actually, this story starts from my FPV plane passion. So I just developed this plane just 15 years ago. So, and it was really interesting plane. So, and I just tried to sell as a kit. So I sold a couple of hundred units in Turkey. So, and then I just tried to do some another parts for the FPV kits. And I just developed this Go Protect kit. So I just protect the GoPro lens if you crash your planes, so you can easily replace the Go Protect kit. So then after that, we just decided to make some plastic parts for our FPV planes, but we didn't find any 3D printing community in our country. And then we decided to go build our 3D printer. So, and then I just talked with my friends. So they comes from the industrial designer and engineering. So we just start to do something. And as you can see that we have so many things on that, but nothing is done. So, and then we ordered first parts from the AliExpress, and this is our first printer. So, because at that time you can't find easily belts, pulley, and everything in the market. So, which is like 2010, I guess. And then I just saw some fruit basket, and then design as a 3D printer. Of course, it didn't work, but we see the movement and everything. It's really well. And we keep going and improve our printers. So we are trying to make a 3D printer from 3D printer. So because that's why I'm telling, we can find the belts or something like that, and we just print some parts from 3D printing, which is like the pulley and belts, and then we print, we design, and after that, couple of years later, we just released our first prototype as a Zone. So our name was a Zone 3D printer, but it is not easy to find it on the internet because the domain was zone3dprinter.com. It's so big, so that's why we change our name and get some investment from some angel investors and create a new company from Zack's. And these printers are our first products. So we developed X1 and X1 Plus, and then also our slicer, which is Cura-based. So we would like to make a printer working with the Wi-Fi, smart and really accessible. So that's why in 2016 we released our X1 series, which is working with the Wi-Fi, touchscreen and USB sticks. It is really sounds interesting because there is no Wi-Fi and USB option at these dates. So, and we also add our UI to the Cura slicer, and we add some machine carousel over here. So if you just connect it to the same network, the machine and printer will be found and attached automatically. And there's a handshake button over here if you want to see which printer is your printer, so you can just press it and your printer is just start shaking and you can easily find and print your printer. Because our idea is that printers have to be smart and the manufacturing will be much more easy for everyone. So then after that, we just designed Z1 Plus printers. And then a couple of years later, right now, we are operating 1,015 square meter place with 40 people, so which is really big for us. And we just released the Z3S. If you want to check out it, our booth is really close, this booth. So right now we released the Z3S. It is smart, smooth, and speed. We just jump to the speed train. and let's show that the video. Press that. No, it didn't work. This is much more easy way. We can show it. I can open on the. That's Murphy. Yes, this is our latest version printer. So we call Z3S. It has 500 millimeter per second printing capacity. Let me just close it. Yes, it has 500 millimeter per second print speed at the 20K, under the 20K, and AI, smooth, arc welder, and everything is inside the printer. It just click and print it, everything. Thank you very much.
Thank you very much indeed. So the next talk will be at 3 o'clock.
So, before we move on to our next talk, we have kindly had this Voron V0 printer donated by Cybor, the guys just through in the North Hall on the right-hand side as you go in. They've had people putting their names onto little post-it notes and the names and phone numbers, etc. So I'm going to do a quick hand into the box of destiny and pull out somebody's name. If they're not here, then we'll contact them and we'll get in touch and it will be shipped to them. But if you are here, then you're very welcome to come and pick it up today. So, right, with no further ado. Only one. Right, I think that's one. Two there. So sticky. We've got Alex. Alex with no second name, just Alex. Telephone number ends in 020. Alex, are you here? Alex, 020. I'm not going to put my hand back in there. This is it. This is the owner of this. We will be contacting you if you're not here. Yeah, congratulations. You're now the owner of this beautiful little printer. Well done. Woo. Cool. Is that right? Thank you. Super. Thank you very much. Cheers. Right, I'll hand over to Phil.
Good afternoon again. So, pleasure to introduce you. Next up on stage, we welcome Mohamed Enis Tareulu from F3DM to the stage. F3DM is a high-precision filaments manufacturer. Enis is going to share his insights on filament in his talk, Printed to Perfection, how filament precision defines the outcome. So, welcome Enis. I'll hand over to you.
Very much. So, I'm Enis from. So guys, I'm Enis from F3DM. We specialize in additive manufacturing filaments. So what we do is we do things a little bit differently. So at F3DM, we are, international company that we are based in UK, Germany, Turkey, and also in Dubai and Canada and USA. So we have established a lot of relationships with a lot of brands throughout the world. So that's what we are strong with. Also, most importantly, we manufacture the best filaments. That's a bold claim, and we have a way to, we have evidence about that as well. If you have time, come by our booth and see the filaments and the results of that. So, F3DM's history. We are established in Turkey at 2017, and by that time, we started reselling printers through Turkey. Then we started manufacturing filaments at 2021 in January. Then we expanded globally, starting with UK, and then we are planning to release the best filament possible, best PLA, high temperature and high speed one. That's going to be a monstrous filament, and I think that's going to destroy the market. So, what is required for perfection in the prints? You need tuned printers, carefully designed parts, and you need sliced profiles, and you need good filaments. So, perfection comes with precision. About that part of the filaments, you need production stability in every batch, and you need industry-best diameter accuracy. So we are able to produce filaments down to 10 microns of diameter tolerance. We're able to do that with 3-axis lasers everybody else is doing it with 2. So we know our filament is round and perfect. And you need good facilities that you know there is no dust and dirtiness. So your filament doesn't clog the nozzles of your, customers. So, and there's one more important stuff as well, coffee. So, what materials do we make? We make mostly everything except ABS and ASA. So right now we have PLA and PTG. Our PTG is food safe grade, but it needs to go through like a capable printer to be that. We also have polycarbonate, which is medical grade, and we also manufacture filaments for defense military. So for those ones, you can contact us because we don't sell them on our website directly. Other than that, we're going to release new filament lines as well. Those are PETG high temperature, PLA high temperature, and recycled PTG. They will be released this year in January. So you can check our website for them. So this is our production video. You can see our raw materials here. This is a dosing mechanism. This is our proprietary laser that we measure. And this is our perfect winding. Thank you very much for your time, guys. This is my contact information. Thank you for your time.
Ladies and gentlemen, how are we all? Good? Hey, super. Right then, so this is the final bit of of this weekend, and I'm going to draw things to a bit of a close. So as I talk to you, I'm talking to you with kind of three hats on. My first hat is a trustee of the SMF that we set up very recently. It's just got its charitable status, which is absolutely fantastic. I'm also talking to you as an employee, as the founder of E3D, along with Sanjay and Josh, more than a decade ago. How time has flown. And I'm also talking to you as a friend of Sanjay. I'm very sad that, unfortunately, Josh can't be here at the moment. He's gone to go and get our van to help us load up. So this is going to be it's a bit of a best man speech. Chula did an incredible speech yesterday morning and this morning, opening this event and giving you a background about the SMF, what we're here doing, why we're doing it, and why we're all joined here at Smurf, which is the first UK RepRap Festival, and by no means the last. I hope this will occur again next year. So, yes, I very much look forward to that. I just give you a very brief background because on Sanjay and how Sanjay and I met. So Sanjay and I met, like I said, more than 10 years ago now. We met at university in Exeter, whilst we were doing our PGCE courses, learning how to be secondary school teachers. And I came across this mad guy who said to me that there was this really weird thing that you can get that makes stuff. And Shamala did a very good job of describing that to everybody yesterday, which was a really lovely and touching speech that she did. So Sanjay grew up down in Devon, which is about 4 hours away from here, in a tiny little village that probably most people have never heard of, Tiverton. Yes, good old Tiverton. And Shamala went through his early life. He went to Exeter University, like I said, with myself, and we decided to set up E3D after teaching for about a year. Although we love teaching and molding the minds of tomorrow, we realized that actually running E3D was kind of pretty cool, and we were doing really well. So we kept doing that, and it has grown strength to strength ever since then. Employing hundreds of people over the years, which has been really lovely, and many of which I've seen here over the last couple of days, which has been really lovely to see. And I've heard some very, very touching stories as to how Sanjay affected people's lives, how he motivated them, how he was the person who enabled them to come out of their shell. It's been a really, really lovely thing to hear over the last few days. So we then also kind of created this community, and this community has joined around us over the last few years. We've got some incredible RepRap festivals that happen in America mainly. The people that join these festivals and that come along, obviously all of you guys here are the ones that make these festivals what they are. It's a real testament to each and every person here as to how accepting we are of one another, of one another's intricacies and oddities, which often come from varying neurodivergencies. So I would just like to do a massive thank you to everybody who has donated over the weekend. We've had people being more generous than I could ever wish for. We've had people giving away printers, hundreds and hundreds of pounds worth of filament and nozzles and boards and just everything, as well as time. And it's been a really, really humbling experience to be here and to be able to help manage that. I say manage that. I have done nothing to do with the management of this, and I'll come on to that in a moment. So a massive thank you to Joel first for running our auction yesterday evening. So we raised more than £21,000 yesterday evening, which is incredible. Thank you so much for everybody who donated bits and pieces to that. It was a really good event. And then Grant, thank you so much for allowing us to shave off your beautiful locks. And I actually, you know what? I think that you look really good now. There's a little bald patch on the side of Grant's head that is totally my fault. It's a bit of a weird, misshapen RepRap logo, but hopefully that'll grow out. So thank you so much. We raised about $6,000 for that. So thank you so much, Grant. We've also raised hundreds and hundreds and hundreds of pounds through the raffle tickets, and I must say that I've really enjoyed actually running the raffle last time. I think if everything goes horribly wrong, maybe I'll get into bingo as my next career. We've also had more than 1,000 people walk through the doors downstairs, which is, again, testament to every single person here and the exhibitors, and you are all just incredible. So thank you all so much. Actually, one piece I was going to say then is about the ages of people that we've seen here. I brought my 2 little boys along yesterday, and I've seen throughout yesterday and today so many young people walking around and getting really into all of the bits and pieces that people have got on their stands, sometimes dropping them, breaking them, things like that. So I do apologize if anybody's broken stuff, but it's for a good cause, right? Because we are like these young people that we've got walking around are genuinely the people that are going to be stood up here in many years' time doing stuff like this, and sat in your seats running companies, being CEOs of incredible tech businesses. So let's continue to help those people, and it's just really, really lovely atmosphere. So thank you for making them all very, very welcome. I guess in closing, more thanks. It's just thanks coming out of everywhere, really. So first of all, I would like to do an enormous thank you to Chula and Georgia from E3D. Who have been working tirelessly into late nights to get this thing planned. It is not a mean feat running a RepRap Festival like this, as you can probably imagine. And from the bottom of my heart, thank you so much to both of you. And it's not just these two, it's everybody else within that, whether it be E3D or in the wider community who has really lent into this event and helped out. So again, thank you so much to everybody. I'd also like to thank all of our sponsors. On the back of my t-shirt, here they all are. There are way too many people to call out individually, as well as our content creators who have spread the word about this event worldwide. So again, thank you all so much for what you've done over the last couple of days. People have been coming here from all over the world. There isn't a continent that people haven't traveled from. And I know with E3D, we send people over to America and around the world. The amount of effort that you've got to put in to transport stuff to a different country is immense. So again, thank you so much for putting in the effort and coming here. And I must say, I think that this has been the best RepRap event ever. Potentially. Definitely the best party last night. I don't know about anybody else, but it was very, very good fun. And yes, so I would be forever grateful if everybody could continue to push forward the mission that we have started here. It's not just the SMF, it's helping out friends and family, it's getting people into 3D printing that maybe didn't know about it before. If they have a neurodivergent difference, then you are the people that will be there to help them. And if they can be helped with funding, if they can be helped with materials or hardware or anything, ask them to get in touch with us and we should be able to help, all right? We'll be running the next kind of round of things in a few months, but we will, in a few months' time, once the dust has settled from this event. Couple of last little bits of admin stuff. So if you won anything or bought anything, in the auction yesterday, could you go and pick it up if you have not already from the exhibitors that have been donating it? And for the exhibitors, would you just mind double checking that these people have obviously donated correctly or paid their bits and pieces? And then happy for those bits and pieces to head off. It will be less to pack in vans. I'd also really like to remind everyone to keep following us on various social media platforms. and keep up to date with what we're doing on that, which will be amazing. Oh my God, I'm pretty impressed that I've not actually cried, because I'm a pretty emotional chap, but this will probably start it off. So, there is one last thing, and it's lyrics to a song. So there is no life I know to compare with pure imagination. Living there, you'll be free, if you truly wish to be. If you want to view paradise, simply look around, and we can do that here, right? This is an example of paradise. Anything you want to do, you can do it. And if you want to change the world, there is nothing to it. Thank you all very much for coming. Woohoo! That's a wrap.